Hello. Good morning, everybody. Let's see. There we go. Yeah, good morning. How are you guys? Hello, LJMF. Welcome to the stream. There we go. Morning. Yeah, I'm from Norway, but my sleeping cycle is beyond shit. So I just woke up I think at 12 p.m. 12 a.m. I woke up. I'm going to go into bed like 3 a.m., 4 a.m. So that's not good. I have to fix it. Hello, Poison. Welcome to the stream. Richan, welcome. Alright. Yeah, we had a long stream, I think yesterday. No, 2 days ago. Yesterday I had to do some work. I think we actually did it. We were able to compile this now. So we have some variables, we have some, we have a function, and the function isn't really doing anything right now. So that's gonna be the first thing we're gonna fix now. Like function arguments, multiple functions, yeah, like calling convention and stuff like that. Yeah, but like as I said, variables are working, and also type defs are assumably working. It depends a little bit. If you're ordering this wrong, it's not gonna work. So like nested type defs doesn't work. Are you using a new theme? Yeah, I am. I'm using this one. Everforest Dark. Sounds so nice. It gonna makes you wake up at 6:35. Yeah, I remembered. I'm glad I'm past that stage in life. I'm very happy I'm past that. Yeah. So just to recap, this is now generating. This is generating this assembly code. So we can see that this is compiling like a code unit, a translation unit, whatever. That's one single file. So we're just printing what file it's compiling here. And also, if you're writing some comments between statements, they're going to be placed inside the output file. So we can actually see where things are happening here, which is very, very nice. The thing we doesn't handle is if some idiot comes in here and tries to do my keyboard is laggy here. Gonna unplug it. Let's see. Okay, that's better. If someone comes in here and tries to do like a multi-line comment in here, this doesn't work. So we still have to figure out how to handle that. That's probably just gonna be like a skip comment in all expressions, but it's gonna be placed like all over the place. Or maybe we can make a function inside the Lexer, which is doing this, handling this. I don't know. I can't change themes because every time I change theme, I keep changing and never make a decision. That's right. But I have like a theme I usually like, but that hasn't any colors. So I like to actually use this gray theme, I think. This I like. Just black and white, and if I'm coding at night, I usually choose this one. So almost no colors. I feel that's the best. I don't know. Fuck, which did I use again? Everforce, I think I used. Yeah, it's a really cool theme. VS Code issue. Just one blind. Yeah, I'm sorry. Anyway, so this is working. We can actually return variables from the function. And let me just get open a terminal so we can see that this is working. Let's see here. And also, we fixed the printing last time, so we have a print which is handling everything we can compile now. So we can visualize how this program is gonna look. So we can see like we have a function here, no arguments. We have a compound statement, which is 2 expressions and a return statement there. And we can see the error 244, and that's basically what this is returning, modulo 256 or something. And we have type defs, so I'm using this operator here for type def. So if I want to have like a token, or let's say I want to have an IPv4, which is a U32, I can just type it like this, and then I can, for example, make an IP address, which is an IPv4, and say it's equal to 56, and I can just return this IP address, and it should give me 56, and it does. So type defs are working. We're gonna do something similar with structures, because they're also essentially type defs. Yeah, last time I were using Linux. I just installed Linux yesterday actually, because I needed it for some networking stuff. Apparently you can't change any network adapter settings on Windows. Like I tried for many hours how to set up a DHCP server on Windows. Like I think that's easy, but on a specific adapter, that seems very hard. What type of parser did you end up going with? This is a recursive descent parser. It is a really simple one. It's at, let's see, 500 lines now. Yeah, so today we're gonna take a look at function calls. We're gonna call into C functions, which we're gonna link in. So I'm gonna be able to write C functions here. And we're gonna be able to call them from our code, hopefully. And yeah, so like calling functions I want to fix, and take a look at pointers. So how do pointers work? And if that's working, I want to take a look at structures. So parsing structures and stuff like that. So that's gonna be cool. But first let's just recap how this actually works. Nothing like, I'm just gonna go through really quickly how things work, so we can get an idea of how this project is structured. Is the font size okay? Or should I have it like this? This or this? Big or small? Moin? Yeah, these are great color themes. I think I've been using those. Okay, we're gonna go with small. Actually, let's switch to something else first. Something a little easier to look at. I'm gonna be using this one. I'm not reading any books. In general, I'm never reading any books. I'm just trying myself. Operating systems, that's really just... I feel that the most difficult thing is the context switch. That isn't really the most difficult thing, but once you have nailed that, it is much simpler to just fix the rest. So, but I haven't read any books. We're gonna make an operating system in this language here, once it's done. Anyway, it all starts in the lexer. So we have a few functions which is being called from the parser all the time. So once the parser wants to do something, it's gonna call one of these functions here. And the thing is that this doesn't allocate any tokens. So we have a token structure, which is sort of describing like a punctuation, comment, whatever. And we have this tiny token cache here. So the lexer object is keeping, I think, like 20 tokens here. And all these functions here are just picking one of these tokens, and it's calling a function for updating that token with the next one. So that function is here. It is here. So all these functions do is call this function here with a specific token. And this will just skip the white spaces. It will check if this is the last one. If the char is a number, it will figure out what number it is. If this is a opening comment, it will parse the comments. If it's a valid letter, it will parse an identifier or a name or something. And if none of these are working, it is going to try to parse the punctuation. And if this doesn't work, then the token kind won't change and this will give an error. So we have to either fix the lexer or we have some kind of error. So this will probably have like a different error reporting mechanism here. Yeah. So that is what's giving the parser the tokens. And then we have the parser, which is starting down here. And this is parsing the entire program. And since we don't have any, like there is many things I want to implement which are not currently implemented. So this is just calling parse1 code unit, which is the one file we have here. So this is only parsing one code unit here. And this is again calling parse a block, which is the same as parse a compound statement. So the difference between parse a block and parse a compound statement is that the parse block doesn't have these curly braces. And the reason is that when we're gonna parse this entire file, we don't have any like curly braces on the end here and on the start. And since we don't have that, we have a separate function for it. Yeah, so this is just calling into try parse declaration or statement, which is often just going in here. And a statement can either be a new compound statement, like this, or it can be a comment, or it can be a return statement. And if none of these are actually present, it's going to parse an expression statement, which is all these lines you can see here. So if I would say something like, IP address is equal to something, this will be an expression statement, which is being parsed here, which is parsing an expression. And this is like a recursive thing, which is handling the operator precedence and stuff like that, building the tree in the correct way. So that's sort of how it works. There is also one more important thing to notice, and that's all the declarations would just push on the scope. So that if I write something like, let's close this. Let's say I have like variable. This is a U64, and I'm gonna give it a value of 30. Then this is being parsed as first a declaration, which is mapping this variable name to this type. So this is a declaration. And then we have a statement or an expression statement, which is mapping the variable to the value 30. So this is an expression statement. And this doesn't go in the code anywhere. So when we print stuff here, the actual body here doesn't contain anything. Doesn't contain any declarations. We place the declarations down here, and that is because we don't keep them the same place. They are kept completely separated. So this is only for mapping this to a type, basically, and this also has like an offset from the stack frame. So by seeing this, we can look up into the scope, and we can get this mapping here, and then we know the type, and we know the offset and the address, whatever. So this is going on a scope. This is going on the compound statement list. All right. What happens if an expression has more than 2 tokens? Like something like this. This is being handled by the expression parser. So this will just loop as long as the priority rises. No, as long as the priority is constant, it's just gonna loop. No. As long as the priority rises, it's gonna loop. And if the priority falls or is constant, it is gonna return, and it's gonna recurse up again, and then we're gonna have the first function call, which is always gonna loop, because the priority is, this is being called with priority -1, which is always which is always lower than any of these priorities here. So that will just loop forever. So this is like handling anything like this. Wanted to use Bison Yak. I was told not to be honest. I started with making a parser generator. But I'm glad I stopped doing that. Thank you for following Field of Allen. Welcome to the stream. All right. Yeah, so let's start. I can't remember if we're parsing the function arguments correctly. So let's just give some function arguments in here. So I'm going to take in a data, which is a U32, and token, which is a pointer to a token object. Of course, we doesn't know what this is yet. So this will be parsed as an unknown token. Because the parser, when parsing this, the declaration can actually be down here. So the parser doesn't know about this. So this is going to be an unknown token, and then we have to figure that out in a later pass. So I think that will work. Nope. Okay, so we have an error. Variable is not declared. And this error is in the typer. So the typer figures out that this variable is not declared. So let's try to just return data. So then it works. And we can also see the function arguments are having We have a declaration of data, which is an unsigned 4 bytes, and token, which is a pointer to a known token. So we have to resolve this one. And like, this shouldn't happen, because this should be resolved. So if this doesn't resolve itself, we have to give an error somehow. So we're gonna go in there and just fix that right away. So it's a declaration. So when we parse, or when we type a scope, we're gonna go through all the declarations, which is in the variable list, and we're gonna resolve that type. So basically we're resolving this one. So if this is unknown, we're gonna handle it. And if the type is unknown, we're gonna get the unknown name, and we're gonna look it up in the current scope. And this is looking up in scope, and this will recurse down. So this is not really look up in current scope. This will look up in current scope and then look up in the previous scope and so on up onto the global scope. But anyway, we're gonna give an error here. So this is only a type. And a type doesn't have a token, does it? Okay, we have the unknown token, so we can actually report an error on this token there. I'm gonna say like unknown type. So if I now run this, it should work. Okay, we're not doing that. So I guess we don't go into the function. Okay, let's try to declare something here. I'm gonna say Texas AU32. Oh, wait a second. We're gonna give it to some unknown token here. So now it's typing the token. It tries to figure out, this is an unknown type, and it tries to figure out what this type is. And for some reason it doesn't do that with the function arguments. Did you thought using some testing framework to validate your code, the code while coding? We're gonna do that now, actually, later today. So I want to write some assertions here. I want to be able to automatically check if something is working, or more specifically, if something is not working. So what we're gonna be doing, we're gonna just write an assertion function in C and just call it. Or we can probably write it in our own language here. We can probably make an assert here, but then we have to make the assert in all the source files, because we can't include files yet. Yeah, that's a really good point. We're gonna have automated testing here. So the thing is that this is one scope. So when I'm parsing a function, I'm opening a new scope here in the argument list. And each of these declarations, variable declarations, is going on that scope. And when done parsing this line, I'm opening a new scope for the compound statements. So I'm thinking maybe I'm not handling or typing this function scope there. So I'm typing a code unit, this is just typing the global scope. This is typing everything. And that typer is going through the functions, and for each function, I'm doing this. So you can see I'm actually just typing the compound scope here. Enter scope. So this is going to be a little bit weird. Okay, so we're gonna still be doing this. We're gonna enter the scope and exit the scope manually. So this is gonna happen before as well. So what we have to do here. We're gonna type the function scope as well. And this will exit and enter this scope. And then we manually enter it here just to get the logic right. Yeah, it's a little bit of an edge case with the functions because we're manually opening a new scope there. But if I now do it, it should work. So we have an error unknown type on line number 3. 1, 2, 3. It seems I'm getting this, but I'm not getting any print. Okay, so where's my print here? Line number 2. I knew there was something funny in the error handling. This is yielding like empty lines. Let's change to 0. That's only giving 2. Okay, so now it's working. So apparently I have to change the number to 2. So some logic here is not working. I think this is because it is very close to line number 0. So that's why it doesn't work. Okay, so now it's working, even though I have 1 here. So there's something wrong when this is very close to the beginning of the file. So we have to sort that out first. Hello, Woody Weasel, welcome to the stream. Criterion to validate the compiler code. I'm not understanding exactly what you're talking about. Hello, Suvu. Suvu, are you from France or something? So it seems like a French name. Welcome to the stream. Hello, Plexcom. Okay. So we're given this token here. We're given a pointer to the capital T and the size of this name. So that's what's gotten in here. And I want to print this line and 3 more lines up. So what I'm doing, I'm iterating through, this is happening 3 times. And I'm backtracking as far. So when this is happening, it won't go past the beginning because I'm tracking the start as well. And while this is not new line. So that pointer is the new line. If that pointer is the new line, I'm doing current minus minus. That's probably not right. Isn't this supposed to happen before? Because if the first character is a new line, it is gonna first subtract it, and then this will be wrong. So I have to first check for that. Let's see if it's working now. So now it's working perfectly. So I can't print 3 lines because I only have 2. I think that was a mistake we did a few days ago. Okay, I'm gonna fix this error handling because I don't like it. It is working though. Actually, Poland. Ah, cool. I don't know any like Polish word. I know one. Sowu. I know the pronunciation though. Alright, okay. So we're getting the function arguments. We're getting the function arguments. So we have to make support for 2 things. First we have to check if we can actually make multiple functions. So I'm gonna make a print function here. This is just a test function. And this is gonna return a U64. And this is just gonna return 56. And then, or I'm actually gonna give it 2 parameters. I'm gonna give it A, which is a char. I'm gonna use U64 actually. And a U64 and B. And I'm gonna return A plus B. And this is actually not gonna take in any arguments. And then I simply want to return a test of 4 and 5. So this is supposed to return 9. Yeah. And we're not handling this specific construct here. So we have to first handle or parse function calls. So if I have an identifier and the next one is an open parenthesis, I'm gonna interpret that as a function call. So we're gonna handle that in the parser first. General questions about C or programming in general, welcome. Yeah, of course. Of course they are. Okay, so this is in the parser. We're gonna go in there. Let's say data is a U64 and it's equal to test. Or let's do this. So this is an expression, and every expression is just handled here. This is handling everything. Even assigned statements are handled there because they're going to evaluate to some value. So you're allowed to do something like this, or maybe a different variable there. That's fine. I'm not going to use it, but it's going to work. And this is parsing a unary expression first, and this is the function which is parsing sort of the main parts in the expression. So if I have like a few more factors, then each of these terms are going to be a unary expression. And then we have the binary operator between. So this entire function call is going to be a unary expression parsed in here. And this is actually where we're parsing the parenthesized sub-expression. So if you have like, if you want to force the order in some way, like this, that's being happening here. So this is just recursively calling parse expression again. So we might have some prefix expressions here, some pointers, some address operators, like unary plus and unary minus. Probably not now. They're gonna make the parser a little bit more complicated. So I'm just gonna support these two, and we're gonna support this. So this is parsing a primary expression, and the primary expression is doing this. So where am I calling? Where am I calling? I'm not doing that. Okay, we're not doing that. So this is gonna return an expression, and we're gonna just store it. This is primary, which is the test here, and probably the things before it as well. Or probably just a test. And then we need to handle this. So we have some kind of postfix or prefix, suffix expression, which we have to parse. Parse primary. I'm gonna make it here. Thank you for following, by the way. Welcome to the stream. This is gonna return an expression. This is parsing a suffix expression, and we're gonna link this with the primary expression. So we're gonna take that as an argument. So I want to take in the previous expression here. Thank you for following. Thank you. Expression. And we need to make some structures for the function call. So I'm gonna go into the tree, and this is where I'm defining all these structures, data structures. So we're gonna work with a type on expression. So we have binary, unary, primary. I'm also gonna add call or function call. I'm gonna say call. It's a call expression. So here we need to have like a name, but this might be more than just a name, right? Because a call expression might be something more complicated. We could have, for example, like a function pointer. Like if I have a function pointer in some kind of array, I should be able to do, I want the array of 5, which is a function pointer, and then call it. In other words, this here isn't just an identifier, isn't just a name. This is in fact an expression. And if I do this before it, I don't know if that's supposed to happen first. I don't know how it's in C. I think we're gonna make the binding here harder. So this is gonna happen first, and then you take the array, and then you take the function call. Isn't that right? In that case, this is gonna be an expression. It's gonna be a call expression. Why suffix? Why not unary? We have unary. Unary is like kind of a suffix plus prefix plus primary. Is it good practice to forward declare all types in a single file? I usually just forward declare the things I need. Are you thinking about like stuff like this? The thing is that I don't want to do the type def. If I had to do type def, it would have been like type def. How is it like type def struct and then give it a name? The problem here is that if you want to use this, if you want to make some kind of linked list, if I want to have a token pointer here, I can't do this because the token is defined down there and the C compiler doesn't know that. So here I have to like say token, and then I have to use the struct token pointer here. And this is this is getting messy. So that's why I'm forward declaring all the type defs in my file. And I know everyone is going to be having a unique name. I would expect to deref something that returns. Yeah. Yeah, so the type def file is just something that I like to do. As long as you know everything has a unique name here, and it doesn't care where this is being included, I think it's fine to do it like this. I think it's getting cleaner, especially when I have like a lot of structures. And this is just a beginning. Yeah, I don't know if I'm gonna do methods on objects. I have to think about it. Anyway, like this is the problem. Like there is not a unique answer on this, and therefore I don't know. We're gonna have the call expression, and we're gonna have a list of arguments, and this is gonna be expressions. So expression arguments. Maybe we're gonna have this token as well. Call token. So I don't know where I'm gonna place this. Probably this is gonna point to the parentheses, or I'm gonna just say token. So this is probably gonna point to the parentheses or something. This is just for error reporting. That's why I'm including this token pointer. And this is whatever's before the first parentheses, and these are the arguments. Thank you for the follow, welcome to the stream. So parse suffix expression, this is getting the previous expression here. So what we need to check if the current token is the open parenthesis, in which we have to parse a call expression. And also this has a list inside it, and I don't like that because this has to be initialized. This is a circular list, and if I don't initialize it, it's gonna give a segfault. So I'm gonna make an allocator, like a new allocate function for this call token. So a call is just an expression. And we need an expression kind. So this field here is telling which of these are going to be used. So this field, in this field I have to add the call as well. So now I can just say expression call, and this is going to give me the call object. And then I have to do list init on the call arguments, just to make sure that's being done. So now I can allocate a call token. So I'm going to first check if I have a token like that. So I'm getting the current token. So all these expressions are working on the current token. It is a little bit of a trade-off, I guess. If you want to handle the next token all the time, or if you want to handle the current token all the time. So we're doing that, we're handling the current token. So if I want to parse a compound statement, the pointer is, it is pointing here to the beginning. If I want to point the left hand side of an equal statement, is pointing here. The right hand side is pointing here. So it is not pointing there and then I have to check the next one. I'm always checking the current one. So if the current token is a open parenthesis, we have some kind of call expression. We can probably do if this is not an open parenthesis. Maybe we have more. We have an array. We have array as well, like this. So I'm gonna we have arrays. We have this. Maybe we're gonna add some more cool stuff after. We have plus, minus. So let's add all of them. Oops. Open square. And maybe we have more here as well. So if this is an open parenthesis or an open square, we have to skip that token. So we have to skip this one. So instead, we're gonna do consume token. So we're assuming that this is one of those. And if it's not, I'm gonna undo this change. I'm just gonna return the previous token. So if either this or this is happening and the token is already pointing to the next element. So in case of an open square, this is pointing to the expression inside the square brackets. And if it's an open parenthesis, it's either pointing to the first argument or to the close parenthesis in case of no function arguments. So we're gonna handle that. So we're allocating a new call here. If this is a function call, I probably want to comment this as well. This is a function call, while this is some kind of array. Should I call story name arguments and return type? Yeah, a call should store the name argument and return type. Not necessarily the return type. I mean, this is going to be looked up. So from this name, the compiler is going to know the type of this, the declaration here. And from that it knows the return type and anything. So we're going to have to do some type checking here. So we have to see what this is going to return. Will you have nested functions? Yeah, of course. I think that's going to be working now. If I haven't done too much here, I think it should be working now, actually. It can be parsed, I think. Parse unary, parse primary. Let's return primary and test with a local function. We can see if the tree is right. Yeah, so we have a function and we have a new function called main, and the main is containing another function. So it gets parsed right. And also it's added to the correct place. So this test will not be visible from the outside here. So I can only call test inside this function. And if I call the test function here, or here, that doesn't matter. So the or doesn't matter. The same way I can say data is equal to something here, and I can declare data down there. That's totally fine. You probably shouldn't do it because it's hard to follow the code, but it's not gonna fail. Yeah. As in closures. As in closures. I don't know what the closure is. I don't know what the name implies. If you pull the variable declaration out of the code flow, can you do subscopes? What do you mean by that? To a separate section? Like in the same function, or let a if condition, I don't know. That's a one-liner if. I don't know if we're gonna have it. I use it sometimes, but we'll have to see. This makes zero sense. I don't know if I'm gonna, that's not gonna be the first priority, I think. The if expressions or ternary expressions. Is that the thing which is called, like, I thought it was called, yeah, probably ternary. Yeah, all right. So we have a call here. We want to parse the arguments. We know the list is initialized. So we're gonna parse the argument while, so I'm gonna say while I'm consuming the token here. And then we're gonna get the current one. So I'm gonna say token equals current token. And while token kind is not equal to token open, no, token close parenthesis. So if this is like an empty call, then this token will be the close parenthesis, so it will just return here. So while that's not this, and we should probably check for end of file as well. So while that's true, we're gonna parse each argument. So we're allocating a new expression, and we're calling parse expression, parser, and the init priority. So this is parsing, for example, the 4. And yeah, so we do list add last. Okay, so here we have to think a little bit. I can't really add it to the list without having a list node. So wait a second. We should be having a list node in here, because I have to list these expressions into the call. And I'm probably gonna list multiple expressions anyway. So what I'm gonna do, yeah, I'm gonna add a list node here. Yeah. So now we can just add the list node into the call arguments. So now I'm listing those together, and now we need to check for the comma. So each argument is going to be separated by a comma. So I first have to get the current token. if token kind is not equal to comma, or I'm gonna check for the close parentheses. So if the current token is equal to close parentheses, I'm gonna break. Otherwise, I'm gonna skip the colon. Comma. So basically, if this is the last argument, this will happen. It will just break. If this is not the last argument, it will skip the comma. If it doesn't have the comma here, it will give an error. So this is gonna error if this is not true. So after this, we should have a close parenthesis. So I'm gonna skip the close parenthesis. Where to find day 1 and 2? They're in the story, like as highlights on my Twitch, and I'm also uploading to YouTube. What happens where subscope, inner scope? What happens if t is equal to u64? Yes, that's a good question. So I guess the question was, what happens if I'm doing something like this? So if I have data u64 and data is equal to a char. And this might either be like an if, or just an empty declaration, just an empty scope here. So when the parser sees this opening curly, I can go to where that happens. It's in a statement. So if it sees the open curly, it is going to parse a new compound statement. It's going to parse a new block. And this block is just parsing the block, getting rid of the curly brackets first, and then it's parsing a block, which is the same as a scope. And then we call this function enter scope. So when I see this, I'm going to enter a new scope. And this allocates a new scope, and it makes that scope the current one. And let me show you what the scope is. So a scope is this. So we have these 3 lists of variables, function, and types. So whatever I'm parsing after that, or in that scope, is going to be placed on one of these lists. So we might have a list in this scope which has a declaration for data, and a new list which is having a declaration for this data. So if I'm using data here, I'm going to first look in the current scope for this declaration. And if I don't find it here, I'm going to go to the parent scope. So this will actually find the variable declaration in the same scope first. So it will go with this one. If I don't have that, it doesn't find it here, so it's going to go to the parent scope and search there. And there it finds the declaration. Yeah. Other stuff. 36 snippets. I think it should be the entire thing. I think I selected the entire thing. Let me know if it isn't. It's gonna be on YouTube in like a few hours. When you run a function, are you punching a new scope or on a clean scope? When I'm parsing a function, I'm actually opening 2 scopes. I'm opening one for the function arguments and one for the body. And that's just for the convenience of parsing. So ideally that should go in the same scope, but it is easier to do it like this. Just yeah, and it's better for error reporting, because if I'm declaring, like, I can place them in a temporary list and just merge them together after, because I know the scope of the function. But I don't know. I'm kind of doing it like that currently. Deleting all videos, yeah. YouTube is the best. Yeah, so now when I'm pushing a scope, when we're like parsing like a complex program, each single scope has a list of all the child scopes, and each child scope has a pointer to the parent scope. So this function here, let's see. So this function has a list of all these scopes here. And the reason I need that is because when I'm gonna generate this function, I need to go through all the variable declarations. In other words, I need to go through all these subscopes. So that's why we're having that data structure. And we're having the parent pointer backwards because when I'm going to look up at data, like a variable here, I need to be able to look it up in the parent scope, and so on until I'm hitting the top level scope. So it's sort of like a list, linked list of scopes and a pointer to the previous scope. Let a equals int b is equal to 4. Yeah, that doesn't make any sense. I'm not gonna, yeah. Anyway, where did we stop here? So I want to parse a function call, and that's a pair. Thank you for the follow, welcome to the stream. So we're skipping the close parentheses. So this is basically, we're skipping this one. And that's it. And I need to check if I need to store anything else. I have the expression. No, I don't. I have the arguments though. We parse the arguments here. So what I'm gonna do, I'm gonna say call expression. So the expression I'm actually using to evaluate the function address is going to be the previous. And the call token, I'm going to use this open parenthesis token just for convenience. So I'm going to say copy token. Yeah. And then I'm returning this new call expression. Actually, I'm gonna recursively call because I can have multiple function calls. Maybe this function is returning a function pointer, so I should be able to do it like this. I don't see that's a good thing to do, but I should be able to do it. And if this is returning an array, I should be able to do this. So it might be multiple things after this. So I'm going to recursively call that function. I'm going to call parse suffix expression recursively. Need some previous. So the previous is now going to be the call expression. All right, that's good. That's the function call. Let's do the array expression as well. If I want to do something like data of 45 of data plus 45 minus test of a function call or something. I don't know. It might be complex stuff like this. So I want the element number 45 of this. And then I want element like I want this element from that array again. So what's in this array expression is going to be a new expression. We can have something complex like this inside the square brackets. So you're going to parse that. I'm actually going to convert this to a pointer deref, I think. So instead of writing, for example, data of 50, we're going to convert this to deref data plus 50. So this is the same. Yeah, this is the same. So this is going to be converted to this. And of course, if data is equal to a U32, it means that the data is 4 bytes. If I then do this, this is 4 bytes. So this is obviously going to be replaced by 50 times 4. So in a later pass, when I know all the types in the program, I have to check if this is a pointer and this is a number. And if that's the case, I have to multiply this addition by the size of the pointer. So this is going to in fact be 200. And then this is not going to be a pointer, it's going to be an address. So we want to convert this to a deref. I'm going to have it up here still. Plus 50. So an array expression. Do we have an array expression here? Yeah, we're not going to have this, we're going to have this. So this is a deref, this is a unary expression. So I'm going to allocate a new unary expression. I don't have any unary. Let's allocate a new expression. I'm going to give it the tag unary. So this is supposed to have a kind. So I'm going to set the unary kind to unary. We don't have a unary kind yet. I'm going to make 2 unary kinds. Yeah. So this is having an operator. In this case, I'm probably going to give the wrong operator or something. The unary kind is going to be deref and address. So this is address of. We can say address of. And this is if I do something like, I want the address of data. That's also a unary expression. Shadowing rules from Rust. Yeah, left keyword is nice. I'm not gonna have it though. What's up, Code Rage? Welcome to the stream. How are you doing? I'm doing fine. We're making a compiler. So it's going great. All right. So now we have the address of and deref. And we're gonna set this to a unary deref. So this is gonna be a deref node. And we're gonna set the operator, which is supposed to be the star. That's supposed to be the star, and we don't have the star. We have the opening bracket though. So I think I'm just gonna set it to the opening bracket. That's really only being used in error handling. And we have an expression here. So the operand, which is what the unary operator is operating on. And here I'm gonna parse a new expression. So this operand will be what's ever in here, which is a new binary expression. So I need to allocate a new binary as well. Binary add, binary plus. Yeah, so this operator. And we can probably do that first. So binary. It's a problem because I don't know what the token is. But I'm gonna just say this is also the token there. Copy token, and I don't need to do it 2 times. I'm gonna just assign it to binary token. So I have the same token there. And we have a kind. This is being set by the function call. And we have a left-hand side. So the left-hand side will be the data. And the data will be the previous expression here. So this might also be like something more complex. I'm not sure how this is gonna bind, but it might be like multiple. If I have like something like this, then this expression will be whatever's here. So the left-hand side will be the previous. The right-hand side will be parse a new expression. So this expression will be the expression inside the square brackets. So here I'm gonna parse that. And we're gonna assume it has some in it. That makes sense. So the token is already consumed here. So we can just call parse expression. Thank you for the follow, by the way. Okay. So this is constructing this binary add. And then we're just making this unary deref, which has the operand of the binary. And that's it. Then we're gonna return parse suffix expression with the parser and the previous, which is now the binary, no, the unary. Does this make sense? We're recursively calling here, and we have the end case where this is just returning. So whenever I'm parsing something which is not an operating parenthesis or a square bracket, I'm returning here, and that's going to return up the call stack. Cool, cool, cool. Really nice. I think that's going to work. Array expression. To an offset a deref or something. We're doing this kind of conversion here. So I think that's good. So now the parse unary is going to first parse the primary, and then it's going to call into this function. So I'm going to say return parse suffix from parser and the previous, which is the primary expression. I think that should work. Thank you for following. Welcome to the stream. Of unit variables. Probably. So now it should handle this, not this, but the rest it should be able to handle. So you can see if that's the case. there is probably something in the printer we have to make support for. Implicit declaration of parse suffix expression. We're gonna declare this in the top. Parse expression. Conflicting types. New call. Implicit declaration of new call. So that's in the tree.c file. I'm gonna copy this to the header file as well. All right, so we have an error. And this is the, you can see this is the, the printer is doing something weird again. It is pointing to the closing square bracket. So that is because when we parse the square bracket here, after the expression, we're supposed to expect or skip the ending square bracket. So close square. So that should fix that issue there. And it's parsing it. What the hell? Okay, let's see if this is right. Okay, so I'm doing data is equal to something. It's a binary equal. Okay, so it takes the equal of data, which is up here, and then the other factor is the binary plus, which is probably this one, between the number 5, which is all the way up here, and the binary plus of binary plus. Let me just make this a little bit simpler, because I'm having a lot of pluses here, and we don't really need to test that. So only 2 of these. Okay, that's better. And we're missing a closing. We're missing that one. Okay. So it takes data plus a binary plus. And this is, that is wrong. So the thing is that the binary plus doesn't have 2 operators. The binary plus seems to only be like a unary. And that's because we doesn't print the call expression. So when we print the call expression, that's gonna add a new node up here. And then we have this data of something. So we can see that the data, oh, we have unary none. Okay, so there is a few things we have to fix. We have to make sure this is a unary deref, and we have to print this call expression. So I'm gonna go into the tree printer and fix that. So this is an expression. Print type, print function, print expression. So here we have unary. We have to fix something in there. And then we're gonna add the expression call. So if I have a call expression, I'm gonna get it from the address of expression call. And then I have all the information I need here. I'm not sure how I'm gonna print this. I want to say, I want to make a new node for a call. So first I'm gonna do indented print of call. And then I'm gonna increase the indentation. minus minus. So this indentation minus minus and plus plus, make sure that we doesn't print under the call. We print like shifted to the left, not to the right from call. We're like shifting this in here. So in here, first I want to print the function, the call expression like this. So I'm gonna say, I'm gonna print something again. I'm gonna print indent print expression. And then we're gonna indent again. Why is not the autocomplete working there? Like this. So then we have the expression. So I'm just gonna print the expression here, which is the call expression. Let's see how that's going. We have a new call node. We're not doing a new line on the call. So we have a call, and the expression is an identifier, which is just test. And then after this expression, I want to print the arguments. So also I want to print if there is no arguments there. So in any case I want to print this line. I want to print that line. Which means I have to paint this call indentation. So whatever the indentation is when I'm printing call, I have to save that one. So I'm gonna save the call indentation here. Is equal to indentation. We can actually do it down there. And then just plus plus. Oh, Tugglebit is reading. Hello, Tugglebit. Welcome to the stream, everybody. Thank you very much. It has been such a long time since last time. Thank you very much. How did your stream go? Did you do some Rust development? Some kind of networking thing in Rust? Thank you very much. Hello, Nai. Hi. Welcome to the stream. I'm off to eat. Have a good stream. Thank you very much. And yeah, have a nice dinner or whatever you're gonna eat. Anyway, for the new viewer, like for the new watchers, we're making a compiler. So we can compile simple functions like this. Now we're trying to make support for function calls and an array expressions and pointers, and starting to go into that as well. And when that's working, I think we're going to do control statements like if, while, loops, and stuff like that. That's going to be really simple. Yeah, so now we're just going to try to call this function from that function here. Will arrays decay into pointers? Yeah, they will. What architecture? I'm compiling to x86 right now. So we have an x86 backend, which is just generating x86 assembly. And then we're going to make a backend for ARM later, which is going to generate native binary code. x64. We're doing x64. Yeah, so that's what we're doing. Thank you for the follow. Yeah, so now we're gonna fix the printing. We're actually printing the tree in a cool way like this, and we're trying to make support for call expressions like this. So I need to paint this line here, which is under the call. So I'm saving the call indentation when printing this, and then we're gonna paint that indentation. So mask of call indentation is equal to true. And so we're printing the expression, and then indented print. So now I want to have either one or two. I want to have either arguments, or I want to have like arguments none. Yeah. So I'm gonna say like if call arguments, I'm gonna check if that list is empty. So list is empty, call arguments, we need a pointer. Then we're gonna print this. Okay, so arguments none. Otherwise, we're gonna print all the arguments. So we're iterating through all the arguments, and each argument is just an expression. Iterator, expression, and list node, I think. So for each of these, we're gonna print. Yeah, we're gonna do this. So we're printing arguments, and then we're printing the actual expression. And then we close the indentation afterwards. And also for this is just going to print one line, so that's fine. Yeah, so if this is the last argument, I'm going to check if expression, or I'm going to check if iterator next equals to call arguments. This is a check I'm using for checking if it's the last element. Then we need to clear the paint mask. False, and we're gonna clear it anyway at the very end here. So there we go. We have an expression which is test, and we have an argument which is test as well. Are we pushing wrong thing here? Identifier test. We're gonna print the expression instead. So we have a call expression, identifier test, an argument 4, argument 5. And then we have some binary kind which is veiling for some reason. Binary kind. Okay, 98. 98. This is failing. I'm actually going to print the binary kind. Thank you for the follow. Welcome to the stream. Binary kind. So we're getting minus something. This is not initialized. So somewhere in the code, maybe in the parser, we're not initializing the binary. So we just did this. And this might be the case. No. We're not doing that. The binary kind is wrong. Are we maybe forgetting the break here? There we go. So that's the entire tree. And it seems to work. We have a plus between a call expression and a unary none. Okay, so we have to fix the unit as well. This is supposed to be dref. So we're gonna fix that. I think because x64 calling convention are a lot more fun than x60. Wait, it's a bit too easy. We're gonna do something really simple. We're just gonna use the, I think it's 4 or 6. It's 4 in ARM. I think it's 6 in x86 or x64. We're just gonna push them to the stack and pop it into the argument registers, I think, in the beginning. Do you malloc when you create a new node? I'm mallocing, yeah. So I'm callocing. So I'm making sure that everything is 0. And that helps catching a few of the errors. So it's easier because you can get segmentation fault, for example. It makes it very simple if everything is initialized to 0. Yeah, and I'm not freeing any memory. So the OS is handling that for us. Okay, so the unary expression here is wrong, and that's because I've only the unary kind is none. So if I go into the tree, we can see I've added these unary expressions, but this only says none. So I'm gonna first say this is gonna start with a 1, because then I can assert this as being something if this is not initialized because of the calloc. And then we're gonna say dref or address of. So now I should get a dref error. And let's see if this is actually right compared to what I'm actually doing. So this is gonna dref. Now I'm parsing this expression here. So this big one. So the first thing it's doing is parsing the first expression, which is 45. So it is plussing. Or am I doing this first? What makes sense to do? I have to compute this one first. If I have like something like this, that is basically like 1, 2, 3, 1, 2, 3, 1, 2, 3. Like this. And if I want to have this element here, for example, I'm gonna first do this, and then I'm gonna do this. Isn't that correct? Test plus 3, and test will then be that array. And then you do test plus that again. Now you do this plus 3, which is going to be 2 though. Yeah, so that's right actually. Because this is happening first, and that's why it's like in the middle here. Because we're going to recurse down first. And then the result of that one, which is supposed to be like a little array, like a normal array, is going to increase with this. Which is data plus 45 plus a test. Why isn't this being handled? Oh, we have it here. Yeah, right, okay, so dref, you dref data plus 45. So if this is like a double char pointer, this is gonna yield a char pointer, and then you add that to the expression here, and you deref that. That's going to give a char. Okay, I think that's going to work. We have to fix the types though, so we can see if the types are also working. So normally I would print the type underneath all these things. So I think I'm going to start to annotating a little bit in the tree about the types. So I want to know what type this deref has. So we have a problem in the typer. We have expression not handled. So let's just make sure we have done everything we have to do in the parser. We have this one. We have this one. Let's try to make some address of expressions. This is the address of data. Okay, so we have a token here which is not handled. We can't use this AND symbol. And also, I know multiple other languages are doing that, because this is the address symbol. So I'm taking in the address of a U32, so maybe we can use the same symbol there. Like this. I don't know. I'm going to use this. We're going to add an AND symbol in Elixir first. Has no licenses, so I wonder, play with your code. I don't know. I'm not really into the license stuff. I probably want to add some kind of license, but you can just play with it. Doesn't matter. I'm really just doing this for myself. I strongly doubt this is going to be like the big language. I really doubt it. So yeah, I just want to have something for myself, which I think is nice. And I know how it works, so I can add multiple features if I want to. I think that's a really cool thing. And additionally, if I'm making the compiler, I can make it work on multiple platforms. So if I'm making like a custom OS, it is very simple for me to make the compiler work there. If I would have tried to make GCC work on my own operating system, that would take like years, I think. Are you gonna have tests built into the language? No. I know SIG is using some kind of test features. It's gonna be more like, we're gonna make an interpreter which is able to run some parts of the program at compile time. So maybe we can make some automated tests there. And like sometimes in some of the global variables you want to compute, and that can also be done at compile time. So there is going to be some compile time execution to make things simpler. And yeah, so maybe. Is a GIT backend and I'm too lazy to make a reasonable frontend for testing. And this might be simple enough to retarget. That's cool. I would love you to try that. Really. This is very simple. This is 400 lines. In the Elixir parser is 1,700 lines total. So this is almost nothing. But I figured, yeah, that's totally okay. Yeah, some basic meta programming compile time execution. I know there is other compilers out there at Twitch which is doing some crazy compile time execution. I'm not gonna do that. That is way too difficult. Yeah. Anyway, let's add this is a bitwise OR. Bitwise AND. So this is use of bitwise operators. Bitwise AND. And we're gonna go into the Elixir. And each time I'm gonna get a new token, I'm calling this function here. And this is just skipping the white spaces and checking if it's a number, comment, identifier. If it's none of these, it's gonna parse the punctuation. It's gonna assume that we have some kind of punctuation. So I'm going in there, and here I'm just looking for, I'm comparing this char with this list. So I'm gonna add a new entry, which is gonna be called like and. Okay, I'm just gonna do skip here. Skip punctuation. And this takes in Elixir, it takes in the number of tokens I want to skip. So since this is only one char, I'm gonna skip one. And the token I want to configure, and the type I want to have. So bitwise and. So this is gonna add this one. And if I want to have like logical and, we don't have that. Yeah, but then I probably will have like something like this, so if else. So now we should be able to recognize this token bitwise and. And this is a postfix expression, so something before the real expression. So I'm gonna go in the parser. And we're gonna parse the postfix expression. So whatever's here. And this might also be like before some kind of parenthesis. So I want it to be handled in here, and then we're gonna recursively call this parse the unary expression. And this is just gonna return, yeah, so this is gonna be called once. Parse primary and suffix. So we have to have return statements on all of these statements here, on all of these cases. So if token is equal to bitwise and, we do something. And token, let's say plus. So this is, no, multiplication is going to be. Multiplication. So this will be a deref. And this will be address. And maybe we're going to just change that because I don't like it. Maybe I'm going to have this I'm going to use this for the deref symbol and this for the address symbol. So we have like some variable has type, this is an address of a U32, and you give it the address of this expression. So this is a little cleaner. And then if I want to deref something, I want to know what's at the address of data. I have to do like data. Or is it better to do like this? Take in an address of U32 and do this. I'm probably gonna do this. Our REST has compiler flags for tests. That's cool. I can do something like that. Yeah. Only 50,000 lines. Yes. They don't really need to be that big, I think. I think we're going to be way below 50,000 lines. Probably way below 10,000 lines. Yeah, it's really tiny. Yeah, I have my exams very soon, like in a few weeks. There's going to be a little bit of a break there. And then I have the entire summer. I don't have any job this summer. I have like I'm working like a startup. So I have some work. But I don't know how much time that's gonna take. So I'm really planning to do a lot of work on the compiler this summer. Probably have like a working compiler by the end of this holiday. That would be great. So we can start making an operating system in the autumn. Raid. That was a long time ago. No. We're still making it. And the type if you want to match it. Yeah, okay. So we're gonna try this instead. So if it's a bitwise and, this is the address. No, wait a second. This is the, yes, that's the address. We have to fix the type instead. So I'm gonna go down to the type parser. So here we're just parsing the type. If that is a multiplication, then we do something. This is now really gonna be the token bitwise and. So this is a regular pointer. So bitwise and, that's a pointer. We have to just remember that. Okay, so now this is gonna be right. So make a new expression unary. The unary operator, which is a token, this is equal to this token here. So I'm gonna say to copy token, and the unary expression or operand. This is gonna parse a new expression. It's gonna parse this again. So you're gonna recursive the code down there. And that makes sense. So it's first gonna do that, and then it's gonna, yeah, so that will be from left to right. While the other thing is kind of from right to left. Yeah, okay, I think this is gonna work. That's a parse unary, and we just return this unary expression. And for the deref, we're gonna do something very similar. Wait a second. I actually want to make a new function for allocating a unary expression, because that also has a type. So just to avoid forgetting anything. Because now I forgot to set the type here. So I'm gonna return a unary. Unary kind. All right. So this is allocating a unary based on the kind. Okay, so instead of doing the unary, I'm gonna allocate a new unary based on the unary address of. So then we're getting this token type here. New unary deref. All right. So these are pretty much doing the same thing though. Maybe we can do something with that later. But I think the theme is a little bit hard to see. This is probably better. Keto Classic. I'm gonna use this one. Anyway, let's see if this is working. Segmentation fault, that's perfect. Why the hell do I have a segmentation fault in the parser? This is getting the current. So this will probably just, yeah, this will call itself recursively all the time. So I need to skip the token there. And I'm skipping the token here as well. So what I'm gonna do, I'm gonna actually consume the token. Consume the token, then I don't need to skip it there. And if this doesn't happen, I'm gonna undo the token. So I'm gonna get it back again. And then we have an error. Yeah, we can't really do this. This should be fine though. Yeah, that's working. So this is to verify the last thing here. Thank you for following. Thank you very much. This is a unary deref. So that's this deref. Let's change the numbers. So let's do 2 and 3. So it's gonna take the deref with binary plus number 3. That's this one. And the left-hand side is a new unary of test plus 2. So this is correct. Let's check this one as well. So this will do 3 first, which is the inner. So test plus 3, deref, and then you plus 21, and then you plus and deref. Okay, this is working. So the only thing we have to do now is fix the types, I guess. So each single identifier is going to have a type. So first I want to print that type in the tree here. And I want to print with a different color so we can see what's the actual type and what's the actual expression. So now I think the parser actually is working. So let's make it a little bit simpler. I'm gonna just use, yeah, let's make an example. I want to have like a board, which this is kind of like tic-tac-toe. So this is an array of 3 U64, and then I'm gonna access the last element in each array. Oops. Oh. Like that. I'm gonna set it to some specific value, and then I'm gonna return 0. So this is interesting. We have an error true 3 in the parser. We don't have an exit 3. Exit 3 in the Lexer. We're exiting there, and we're exiting here as well. So this I don't think is happening. If this is happening, I will print something. P count exceeded. So it's not that one. It is in the, it is up here, the base is 10. So it doesn't recognize a number. Why doesn't it recognize a number? I think this is the case where we return 0. So this expect to have something after the 0. So we still need to check if this is, if that's just a 0. We can't really do something like this. That's not allowed. But this should be fine. Thank you for following me. Welcome to the stream. I want to I want to just check if the next is a number. So if the next is a number, I can break. So if base is still equal to 10 and Lexer cursor a 1 is a number, then I'm returning. Am I missing something? Expecting ending. Or is this gonna advance there? Dang it. How do we do this? The best possible way. Are you sure you have cursor 1? Yeah. So cursor is just a chart pointer. So what I have to make sure is that this is not pointing to 0 or just exceeding the range of the actual data. It is ending with a 0, the entire file. Will the O's be written in your language? Yeah, I will rewrite the O's in my language. That's, I think that's gonna be great. If you're not starting by punching holes into paper. That's like 1950 or something, 1960 probably. Flipping switches. Hello, young Scotta. Welcome to the stream. You're rewriting Rust. I don't know how to write Rust. Why do you use Windows with WSL instead of a Linux installation? Because I can't get my mic to work on Linux. I have Linux installed, and I'm using it if I'm gonna do some networking. All right. So really what we want to avoid is having like a number like this. If base is 10, because it might just be a 0, that is fine. I'm gonna check if Lexer cursor is equal to, if Lexer cursor is equal to 0, break. Oh, we should probably just go to fuck. No, I'm gonna say if that is true and this is stupid. I shouldn't use so much time on this. I could just make it work, but I want to have it like in a clean way. How I started programming, I started with Arduino. Started like small microchips for like a few years ago. Like writing drivers, UART drivers, printing stuff. And then I got into operating systems, writing like allocators, OS, threads, processes, just messing around really. And I did a few file systems, I tried a few network stacks, and yeah, I'm really just trying new things. And now I'm trying a compiler. But I started with Arduino. If the Lexer cursor is so in these cases we want to skip the Lexer 2 times. So here's the next one, if the next one is not a number. We're gonna check if the next one is a number. This is not very nice, but I don't care. If the next one if the next one is a number, I'm gonna exit. This should be very simple. Let's do else here. I think I'm gonna do like else. If none of these are true, then I'm gonna make sure it's not a number. Yeah, so if none of these are true and it is still a number, I'm gonna exit. I don't have any, I can probably print parse number failed or something. So that is gonna handle that. I don't care about this. I really don't care. I don't care. Else, if nothing like this is happening, it's gonna return an error if the next one is not a number. Then it's gonna exit, otherwise it's gonna just do it once. Fuck that. This is not a great solution, I know. Parse number failed. Yeah, this is not allowed. Okay, there we go. So it's returning, it is returning number 0. I'm gonna fix that later. It is a very simple task. I just, my brain has stopped. Rust is the most popular language on Twitch. Yeah, I know. It's a safe language. Like Linux is starting to use it as well for the drivers. Okay. Yeah. So we're parsing the types correctly. Let's just look into how the types are declared. So we have a declaration which has the type array of 3, unsigned 8 bytes. So now we're gonna go through the code and we're gonna annotate the tree with all these new types. So if I have like a deref, I'm gonna start propagating the type up the expressions in some cases. And then we're gonna have in the printer, we're gonna check if the expression does have a type, I'm gonna print it. So that's for the expression. And if it's a binary, I probably want to print it above the binary in some kind of different colors. I'm gonna do yellow or something. Print function print type. So here I'm just breaking. And this is unknown. I'm gonna mark this as yellow or something. Do I have like colors? I don't think so. Print color Linux C. Okay, so color in normal, I guess. Color red, color green. I'm gonna use. I'm gonna just take them all. We're gonna just add it up here. I'm not really gonna do this on stream. Fix this. So we want to print color green. Let's try color green. NRM. All right. Because you're getting this. I don't like this. I want to have this in a color. And I want to remove the color here. And I guess that's very difficult because I'm having a function for printing these indentations. So I'm gonna make a new indented print with a color. So I'm gonna say colored indented print, and I'm gonna give that char pointer, which is the color. Let's just copy this. Colored indented print. I'm just gonna copy. There is probably, I can probably just do a function call there. But first, I'm gonna print the string, which is the color. And then we print normal again. I think after this. So this will be a k like n NRM. Does that work? I'm gonna fix that later. So we have to call colored indented print. Print type that is a pointer to I'm gonna, I just want to make this work. NRM, and we're gonna pass this in here. That's everything. That's almost. It is almost. It kind of works here. Indented print. We're probably failing to set it to 0 again. Just printing the buffer. That's a null pointer. Green, green, green. Color. That's strange. The most important thing. It is going to be important because we're going to annotate these types all over the place. So I guess it's going to be very, very complicated if we don't print the colors. I'm going to use something very close to C regarding the syntax. This is working perfectly because we're not printing those. Thank you for the follows, by the way. We're printing this first. Let us just clear the thing after. Okay, there we go. Okay, so we have declaration A and we have the print in green. So everything which is green is a type. So now I want to annotate all these things with the type as well. So I want to probably do it below. So this is an expression, this is an expression. I want to do it below. There is really no like good way of printing that type. Yeah, I'm gonna print it underneath every expression. So if I'm printing an expression, I'm gonna do it over, like above it. So if the expression has a type, we're gonna print the type. So now we should see more, yeah. So now we're starting to fill in these fields. So we have a number which is unsigned 8 bytes, unsigned 8 bytes, unsigned 8. The identifier board, I don't know what that type is going underneath there. That's, yeah. That's because if it's an identifier, I'm printing the type underneath. Which is really, I should do one thing and only that. So I'm guessing if it's an identifier, I'm doing something special. I'm printing the type here, which is really stupid. Okay, so if it's an identifier, this is in the printer, okay. So I'm gonna do it like this. And this is also an expression. So I need to fix this in a typer instead. Okay, so as far as I know, this is, I want it to be like this. It might be a little bit ugly, but that's fine. So now we're going to go into the typer and start typing out these expressions, because we need to do some changes here. So as I said, if you have, let's make a U64 pointer. This is a pointer, this is the address of a U64. If you do test plus 3, that should be transferred to test plus, the size of this is 8, so 24. Because when you generate something, like this can be done in the generator as well. But typically when you generate something, this is just going to transform to an address. And like there is really no such thing as incrementing a pointer. That is just for the compiler. So you have to know how big the pointer is, like what that is supposed to point to, and you have to increase this addition with, you have to multiply that bit with the size of the type. So we need to do this conversion here, and that's going to be done in the typer. So we're going to take a look at that now. Also, primary expressions are supposed to have a type. So if we have a primary expression, which is just an identifier, we're gonna propagate the type to the actual expression. So if I have a primary expression, I'm setting the declaration equal to the declaration, and I'm gonna set the expression type equal to declaration type. So now, oh, ow. This is supposed to be an and symbol. We're doing mistakes already. Let's delete this as well. So this is the address of a U64, which makes sense. So now it's going to start to annotate these identifiers. So this identifier has the type an array of 3, unsigned 8 bytes. Let's do something with this. Let's say like okay, still working. Yeah, so this is what I'm parsing. This is the program. Yeah, you don't need to define the entire thing. You can just start really simple. Like the first day we did only expressions. So only like numbers and plus minus division, multiplication. It was really simple. So you can just start there and just build onto that. What am I doing now? Now this is being transformed from the code into some graphical representation. This is ordered in memory as like a tree. So this is just visualizing how the memory is looking like. And taking, for example, this is the address. This is gonna return what's on this address here. That's the thing. So we can see that this is being converted to this representation here. So this is a deref and it is a plus. And the left-hand side is test and then the right-hand side is 3. So this is going to take test and 3 and it's going to add them together. And then it's going to take the result of that and dereference that. So this has to be an address. So now we need to fix this. So this is going to be converted into something like this. Really size of U64. Or size of whatever test is pointing to. If that makes sense. So this is supposed to be a pointer and you multiply that by the size of what that is pointing to. Is this TDT 4205? What is that? 4205. Is that the line? Is that the subject I'm having? Yeah, this is not like I'm having that subject this year. But unfortunately we're like the focus, it's a good subject, but the focus is a little bit different. And the exercises are, they're using like these Lexer and parser generators, which I don't really like. And like really this entire year, we should be able to compile something that we're going to be able to compile today. So I think by just concentrating and shifting the focus a little bit away from like what the focus used to be like a few years ago, you can actually, because this has been done in like 3 days, we've been able to do this. And that is really all we do in the subject. So I don't think it should take half a year to do what we're doing there. Yeah. BNF. I think this is more clean. Not using any parser generators, just handwriting it. I like that. Yeah. Okay, cool. So now we're gonna switch. We're gonna check if we have anything like this. So we want to go through this entire program. We're gonna do the second pass, and we want to look at all binary expressions. And if the binary operator is plus or minus, and one of the operands are a pointer, we have to do something special. So that we're gonna take a look at now. And because that's gonna like introduce a little bit of a logic, so I'm gonna make a new function for it. So I'm gonna say type type binary expression. So this is going to be where we're going to start. I'm just adding this up here. Yeah, we're just going to call this directly. Thank you for the follow, by the way. Welcome, welcome. So this is giving us a binary expression. This function here is giving us a binary expression. So we're both saving the expression and we are saving the binary pointer. These pointers has the same address, so they're basically pointing to the same object. The expression has also this information here. So the expression has information about the type. So therefore we both have to have this element and we have to have this kind of information there. So we're going to just start by typing the sub-expressions. So if I have like test plus 3, I'm going to first type these expressions here separately. And then I'm going to check what the operator is. So if the binary kind is equal to binary plus, we do something. And binary minus, we do something else. So in case of binary plus, we have to check if one of them are a pointer. So how is this actually working in C? If you have a pointer, since this is a pointer, I don't think you can do this in C. That's an error. You can't add a pointer to a pointer. You can do the subtraction though, and that's going to give you the number of elements between these pointers. Not the number of bytes, but the number of elements. So we're going to divide the difference, the address difference between, then we're going to divide the address difference with the size of the pointer. Okay, so let's take the plus first. So this is undefined, this doesn't work. Test plus 4, that's gonna, we have to post-process this for a little bit. If I have 4 plus test, I'm gonna do the same thing. And if I have 4 plus 4, like a non-pointer plus a non-pointer, I'm just gonna return. I don't do anything. So if this is plus, how do we check if something is a pointer? So we have access to the left and right by this. And these left and right should have a type. They should have a type. So what if this is an inferred type if I don't know the type of this? That's a problem. So we're not gonna support that just yet. So I'm gonna assert that the binary left has a type and that the binary right has a type. And then I should be able to access it like this. So if the binary left kind is not equal to type pointer. So if this left hand side is not a pointer, yeah, and We're probably going to write this a little bit differently, but this is essentially what we're going to check. So if both are not any pointers, we're going to return here. So this is fine. If none are pointers, we're not going to do anything with them. And then we're going to check the case where, let's check this one. And if we have some kind of expression like this, we're going to transform it to this, because it is basically the same. So we can either transform this to this or this to this. But this is what I usually do. So I'm going to transform this one to this one. So I'm going to check if the left one if the left one is not a pointer and the right one is a pointer, okay, so I'm going to make two variables for this. Right kind is this. And left kind is this. So if left kind is not equal to pointer and right kind is not equal to pointer, we're going to return. If left kind is not equal to pointer, but the right kind is equal to a pointer, then we're going to swap this to arms or expressions. This is the type of step where you start getting... Yeah, that's the pointer difference. So this is why it's great to have types in general. One of the reasons. We need to switch the types here. So I'm gonna store the expression temp is equal to binary left, and we're gonna set binary left equal to binary right. And we're going to set binary right equal to temp again. So this is going to swap those two fields. And probably I can also swap these two fields, the left kind and the right kind, just to make sure they are right again. I'm gonna do that. That's not really necessary, but I'm gonna still do it. Right kind. Or we can just update them. I'm just gonna update them. Binary left type kind. Like this. Thank you for following, Wats. Welcome to the stream. So now these are fixed. So basically we can only have either this case or this case. So I'm gonna assume this case, and if it doesn't return there, it's gonna give an error. We can just track that here. That's probably easier. So if left kind is equal to a type pointer and type pointer, error token, I'm gonna give an error on the left hand side. but probably on the plus. I'm gonna give an error on the plus, or the operator. So I'm gonna say binary operator cannot use this operator on pointers. There we go. So now we don't really need this, because now we have only one case. So we're just gonna swap them here. Now we have the case where, like, test plus something, where is a pointer. That's not really good English, I know. So we have to figure out the size of test. And we're gonna multiply this with the size of test. And if this is a constant expression, we can probably just modify that one. I think I just want to do it generically now. Doesn't really matter. Let's just save the size. So this is binary left type size. Assert size. Yes, we're gonna assert that the size is something. So this will be the size of this one. No, that's a pointer. That is a pointer. So what we really have to do, we have to do type pointer to size. So this is going to find whatever this variable is pointing to, what is the size of that one. Because if I was only doing binary left type size, that will be 8, because all pointers have 8 bytes. So this is the correct thing to do. Typo in right kind, type pointer. Thank you very much. That is hard to see that. Thank you. So I'm going to make a new multiplication expression. I'm going to make a new binary. Multiplication is a new binary. We're going to make it a multiplication. So the operator what kind of operator are you going to give them? I think we can change it later. I'm going to just give it the plus operator. So that'll be the binary operator. And we don't need to copy anything because this is already copied. And the multiplication left is equal to binary left. No, this is equal to binary right. So this is the right hand side. So that's the multiplication left. The multiplication right is equal to new number. So new number, primary, something like this. Okay, so I'm first going to make a new primary number. And this is the size of the type, which is what I'm going to multiply this with. So that primary number is going to be the right-hand side of the multiplication, while the left-hand side is going to be assigned to number 45, which is the binary right. And then I'm going to set the binary right equal to this multiplication. So I'm not really doing anything, I'm just swapping the pointers. And this doesn't return anything either. One more thing, are we actually typing an expression here? This is an expression and we're switching on the type. If this is primary, if the number is going to be U64. Since this is a new expression, I'm going to type it as well. I'm going to type both. I'm not sure if I'm going to do it like this. Type expression with the primary, and we're typing the multiplication expression, and we're typing binary expression again. No, we're not, because that will mess up the pointers. We're just gonna do this once. So multiplication, and finally we have to assign the correct type to the actual expression. So if I'm doing this, this is really just a new expression. Yeah, so this is a new expression. And I have to assign the type to this expression here, which will be the same type as this pointer. Thank you for following. So I'm going to say expression type is equal to binary left type. And if we return here, we're still gonna say that. Binary left type. This is not really right. If it's a plus, yeah, this is gonna go do something else. We're just doing this for now. It's gonna have to do some comparison against the type. Let's see if this is working. That worked really well. Type expression primary. That needs some kind of typer. Okay, so this is not the expression. I have to do cast. Okay, we're having an error. This is not allowed. That's fine. So does this work? Declaration board. Oh, we have something. Type binary expression. Assert binary left type and binary right type failed. Okay. So when I'm asserting this, no, I'm asserting it. Where's the assertion? Typer 84. Okay, so binary plus. I'm asserting that both the left-hand side and the right-hand side has a type. So that's why I'm typing the right-hand side and left-hand side first. I'm gonna do two assertions because I want to know which of them are failing. So the left-hand side is failing. So for example, this. So the test here is failing. So this is just a primary expression. I feel like we're not doing the unary thing. We're typing the unary operand and we're gonna update the expression as well. expression type is unary operand type. We're gonna assert this is right. Okay, so there we go. Now we're typing a few more things. It seems to be wrong with the deref, because a deref is not supposed to have the same type. So in case I'm... yeah. So this is not right. We want to assert that the unary expression has a type, and then we're gonna switch on, we're gonna check each of these different unary kinds. So if the unary kind is equal to unary address of deref. So if it's a deref, then the expression type is going to be this pointer to type. This is what it's pointing to because I'm derefing. I have to do the switch here. If it's an address, then I guess it's just a number. No, it is not. Then it's going to be a pointer to. We have to construct a pointer to something. So I have to make a new node here. I have to make a new type actually. I'm gonna make a new type. I'm just gonna call it type, new type. The auto completion are really slow here. Reload window. Thank you for following Volcanic. Welcome to the stream. This is a pointer. Oops. And this also has the right size and so on. So this is a pointer. It doesn't have a count, so it's 0. And it's pointing to the unary operand type. And then we're gonna say this expression type equals this type instead. So I think if I now run this, this is really cool, because now we can actually see when I'm derefing stuff, the deref node has an unsigned 8 bytes. So here I'm actually propagating with pointers and stuff like that. So what am I doing? This is a board. So I'm having like an array of arrays. So board has type array3 of unsigned 8 bytes. Which means if I take board plus something, that's going to still have the same size. But note here that we're actually fixing that. This is wrong though. This is wrong. I know it's wrong. I just don't know how to explain it. You can see we add board, like we add 2 times 8 to board, which is wrong. Because then we're assuming that board is pointing to something which is 8 bytes. Well, the board is pointing to something that is 8 bytes kind of, but it's pointing to something more. So we have to, if this has a size, which is the case for arrays, we have to multiply it by the number of elements. And that is happening, that's in the plus. So in this multiplication, the size of the pointer is really the size times the number of elements. Count. If it is a count. So I'm actually going to check if this is a count. I'm going to do let's make a new variable first. Oops, it didn't work. So I'm saving the count. If we have some kind of count, we're gonna do size multiply by the counts. See if I run this. Okay, this is better. Switch this to 3. So here I'm first accessing the third element on this board. And this is a, I'm gonna say 4 here. So what this is like 3 numbers 4 times. This is what this is pointing to. So when I ask for board of 3, if I just do this, I'm supposed to return a pointer to that, like the element here, number 3. So 0, 1, 2, 3. So this is going to really return this expression at the very end here. And in order for us to do that, we have to add board plus 3 times 24. Because remember, each one of these bits are 8 bytes because it's a U64. That is actually working, and we're multiplying that by 3. Yeah, this is working. Do we have an error? No. So our generator is starting. Okay. We're gonna get back to this. I'm gonna go through it again and just check that everything is correct. Let's get function calls to work first. So I'm gonna say data as a U64, which is test of 5 plus 5 plus 5. So this is supposed to give us 15, and I'm returning data. So I'm calling this function here. Thank you for the follow, by the way. I'm gonna check the chat. I think I'm gonna steal some of this syntax, to be honest. Like, I've stolen this from other places as well. I feel most of the programming languages made today are very similar, like in terms of syntax. So I'm gonna probably use something that I like, and for example, this is from both Go and J, as far as I know. He's also using the double thing here. I like the syntax there, but I don't understand. Like, there was some guy on the stream yesterday who told me what he was using it for, but I'm gonna be using it for typedef. Hello, Giuseppe, welcome to the stream. We need your YouTube address. Thank you, Natsu. I think that's that one. What happened with Unknown? That was an abandoned project. That only included the Lexer. Yo, Volcanic Popsicle. In the chat worked well with a Google. Yeah. Shouldn't you complain that you're trying to set an array to a number? The AND symbol is the address symbol. So for example, I can have a pointer which is an address of a U32, and I can set this, for example, to, like, let's say U64, and then I can set it to the address of data. So this is an address of U64, so I'm setting it to the address of data. So that's sort of pointers. In C, this would have been like something like this. Like, the error messages are not implemented really well yet. I'm gonna get back to that. Because it's constant. All right. Yeah. I like the typedef. The syntax for that I want to use for typedefs. I think that's very clean. And that's going to make anonymous structures and members and stuff like that very simple. And very clean, I would say. Yeah, J. Yeah, you had board, and then you did board 3 is equal to 45. Oh yeah, so that wouldn't work. That would that has to be checked by the typer. That's an error. All right. So I think I've catched up with chat. So now I'm gonna try to implement the like we're gonna go into the generator and actually generate this code for doing the function calls. Yeah. So this is the generator. It is not very long. And we have some kind of, what do you call this? Like some header before the actual function body. So let me open the actual output file. So you can see we're having some header before the function body, and this is just saying that we're gonna emit text, and we have some global variable called test, and this is the function name, and it's doing this, and then we have a label for the end of the function, which is used in the return statement. So whenever I want to return something, I'm just gonna jump to end test. I'm gonna place what I want in RAX, and I'm gonna jump to this label. So that's how I return stuff. This would really be like that. So I guess this text is gonna do a new line first. I want to have a new line before everything, and this jump to end, in case of a return, is not gonna do a new line. It's gonna be like this. Okay, so we have the same thing. If that got generated, okay, we have an expression not handled. That's fine. You can use, yeah, I can use Shift Control B. Didn't I do that? It was because it was on the another thing. So if it's on the search, I can't use the Control Shift. It doesn't work. Like Control B works, but it just toggles the display there. So I have to go and choose Explorer, and then it's back. Say J before. What is it called? Like, how is it pronounced? Jai? Like it's, I guess he wanted to seem like joy. Jai. J. I don't know. I'm from Norway. Yeah. Finnish. Hello from Finland. Scandinavians represent. Yeah, we have like a, ö, å. It's really weird letters. And it sucks because we're actually using those letters all over the place. And I have an English keyboard, and the software for this keyboard doesn't include those letters. At least if I'm using US keyboard, I can't use those letters. I have to like use the entire Norwegian language in order to use those letters. So when I'm like talking with my friends, I'm using O instead of I'm getting complaints about that. Anyway. Yeah. So this is a function. We're going to call this function here. So the first thing we have to do, we have to unroll the arguments. So we're going to place the arguments. I think I have it someplace. Here we go. So this is the calling convention. We're going to use this system v x64. So we're not going to support stack parameter. We're going to only use these registers here. I think we're going to do some more exotic things with the argument parsing later. I got some inspiration from one guy who has also like which is I don't know how to say it. I got some inspiration from one guy, and he told me some cool things with argument parsing. So I'm gonna take a look at that first. But let's do something simple. Let's just use these registers here. Yeah, let's copy those. So I'm gonna place the arguments inside here. Okay, so I'm generating a function. Okay, so first of all, when I'm generating a function, I'm generating the local offsets for all the variables. So basically, when you say any variable, when you see any variable inside here, and this might be either a local variable or like the function arguments, any declaration is gonna be assigned one place at the stack frame. So for example, the variable A or B, they're gonna have their place on the stack frame, which means if I have, for example, the variable B, I should be able to do like arrow and some kind of declaration and some variable declaration, and this is going to have an offset. So this is what I'm using to compute the offset here. So from just this name, like A and B, I'm going to get the offsets. So basically the address where this is stored. Yeah. So I have to go through, I know the address of these entries. So I have to go through all these registers. If I'm having like 2 arguments, I have to place this one at this address, and I have to place this register at this address. So I have to go through the number of arguments. So let's just have a register index. So I'm going to iterate the function scope and variables. This is the correct thing. So the function scope is the scope of this argument list, and this argument list has a variable list which is listing all these declarations. So this will just iterate through all these declarations at the argument. So each of these is a declaration. And each declaration, as I said, has an offset. And this has already been assigned because we're calling this function there. So the declaration has, we have to use the variable entry because we're in the variables list. So the variable has an offset. And we know the offset from that one. So I'm just gonna store the register. This one, this one, this one. Let's make a const char pointer argument registers. So RDI, RSI, RDX, RCX, R8, and R9. So these are the 6 argument registers. Let's have them like this instead. All right. So I'm gonna store this register at this address here. So I'm gonna emit a move instruction. I'm gonna move one of these registers. I'm gonna move. So this is a parenthesis, and then I have to do a string as well. Yeah, it has to be like this. So this is for one percentage sign, and this percentage S is for one of these. And I'm gonna move this to the decimal value and RSP. This is the stack pointer. I'm gonna explain. This is base pointer. So the register I'm gonna use is argument registers of the current register plus plus, and the offset is declaration offsets. So I'm basically moving a register to its assigned place on the stack frame. That's what I'm doing here. So it's 64. Okay. What if this is bigger than 6 arguments? So if I'm gonna allow I'm gonna check up here if this is if reg is bigger or equal to 6. I'm gonna say error token. I'm gonna give an error on the function, I think. And the function has let's give an error on the declaration. And this is supposed to have a name token. So this is going to give an error on this name here. It's going to say that test is having more arguments than 6. All right. So let's see if that's working. If I can. We probably have still this error. So we have an expression which is not handled. We're gonna fix that first. I think this is gonna work. I'm gonna explain what this is doing though. On the stack frame. Okay. You can use a programmable keyboard. I have a programmable keyboard. It was actually on Norwegian first, I think. I can't remember. Yeah, but it's possible to fix. I have to replace all the keys on the keyboard to do that. R8 and R9 are additional registers. I think you have more as well, like I think you have R0 to R15 in x86 as well. I just think that the first like 5 or something are called different things. To 16, okay, to 16, oh yeah, R15. Thank you for the answer there. Bytecode instructions are black magic to me. Six arguments max. Yeah, you shouldn't really use more than 6 arguments anyway. But I'm gonna support more. This is the simplest implementation though. The reason is why I have to pop it in the backward order if I'm gonna add more arguments. So it's gonna be a little bit more. Oh, the language. I should probably change the language there because it's still saying C. The hundreds of 5-row functions if I can only pass it around. 6 arguments. You can parse structures, you know. You can make a big ass structure and just pass that around as a pointer. Okay, let's fix this last thing. So I'm having an expression which is not handled. That's interesting. We're gonna go on up to the expression here. Oops. So primary, unary. Is this actually happening? I think this is happening. So we have a primary expression which is not handled. What kind of primary expression is that? Oops. Okay, that's not the primary, that's just an expression which is not handled. Where's the error? It is just error 1. Expression not handled. Typer? Oh, it's a typer fault. Typer. We have primary, unary, primary. We have call as well, so we have to type call. So if this is a call expression, we should probably say like call. I don't know if we're gonna type anything on the call expression. Yeah, we kind of have to do that because this is like an irregular call. We have to type all the expressions inside it. And then we have to do some checking against the function call. So we're gonna not do the checking against the function call, but we're gonna type all the argument expressions. So this will be expression call, and we're gonna make a new list node, iterator, and each of these arguments are expressions. I'm just gonna call it arguments. And we're gonna type expression with each of these arguments. I think that's it. And then we have to look up the function, and we have to assign the type there. Can we do that now? Because this call expression should have a type. I think we should be able to do that. So I'm gonna look up this declaration in the current scope. Look up in current scope. I'm gonna give it a typer. This is the name. So this needs a little bit more logic, I think. This is perfectly fine if the call expression is just a primary expression. So I'm gonna assert that. Assert that call expression kind is an expression primary, and assert that call expression primary kind is equal to primary identifier. So this asserts that this is like whatever you're using for the call is just a normal identifier. And then you can look up that identifier. So call expression primary name. We're going to use this for the lookup. And the declaration kind is declaration function. Actually, let's make this a name so I can print what it's doing. Like this. Thank you for the follow. Thank you very much. So now we're telling if we're looking up a function. And if declaration, actually we're going to assert that the declaration is something. Or we can just give an error. If not declaration, error token, call, I'm gonna give the primary token there. Yeah. So I'm gonna say expression primary token. Function not found. So after this, we have a new declaration. I'm gonna clean up the code a little bit after this because I don't like it as it is. And the declaration is a function and it has a return type. And this is gonna be the expression return type. Is equal to declaration function return type. Let's see if that's better. Okay, so it's generating the actual code there as well. Implicit declaration of error token. Where is that? Is that in generator? There we go. So now if I change it to something else, which is not defined, I'm gonna have an error. Yeah, the line is a little bit messed up, but it basically said the function is not found. It doesn't find the function test. So if we're just doing this, I think it also is gonna tell me what the function is gonna return. So you can see that this call expression is returning 8 bytes here. If I was to change this to like a pointer of 45 U64s, no, that's not the pointer. A pointer of that, it is going to say that this call expression is returning this. So that's working as expected. So all we have to do is fix this assembler issue. Complaints about junk after RBP. On what line? Output line 4. Yeah, this is before the function. So this should probably go after here. Actually, it's going to go after we set up the stack frame. Yeah, and we need a percentage sign here as well. Thank you for the follow. Thank you very much. Yeah. So this is gonna go after this sort of header. So this is where we set up the stack frame. And then we're gonna fill in the registers and assign them to the stack frame. And this is supposed to be percentage. That's gonna print the. It's gonna print that. And that's it. So this is better. It is assigning those variables to the stack frame. And I'm having like minus 16 here. Why is that minus 16? Computing local variables. I'm gonna print what I'm computing here. So I'm gonna print whatever I'm assigning. So I want to print an assigning on stack, and I'm gonna print the name, and I'm gonna print the offsets. Assigning a name to an offset. So there's a declaration name size, declaration name text, and a declaration variable offset. Something like that. So I'm assigning data to -4. What the hell is a -4? Oh, this is probably this one. So that is -4. Okay, so this gets assigned first. That's probably fine. So this gets assigned a -4 because this is a 4-byte number. And then you're assigning -16 and -24, so that's right. So you're moving those arguments into the correct registers. All right. Seems to work. I'm actually going to do this. So this is argument registers, which means that if I'm calling that function now, it should work. I have to do 2 more things. First of all, I have to fix the call expression. So when I'm going to call something, like if I'm down here, if I'm going to call this function test, I have to make sure I place the correct content in RDI and RSI, and then I have to just jump to this label. And that's supposed to happen if I'm having a call expression. And I should like be checking the argument numbers and stuff like that, but that's going to happen later. So this is going to happen inside the expression. See if I'm having an expression, I'm going to make a default case first. Generator expression kind is not handle, and a new line. Well, let's return just an error. So if I now run this, is going to give us an error because we have an expression kind which is not handled, which is the call expression. So we have to handle this. Expression call break. Six registers, 6 arguments. Yeah. You can do file line just to make it simpler. Yeah, I can do file line for typer is what's like a type checker. Type checking. Break is over. It is just checking typos and copy the variables. Yeah. Yeah, so I'm coding here in C, but I'm making a new language. I think Luxor is a kind of cool name. I like it. I actually wanted to be called Lux. I don't know, because I like the extension. But Lux is actually taken. It is a compiler already. Is Typer doing the fancy tree output? The tree output is generated from two places. So the first pass, which is the generator, no, the parser is generating this thing. So this is the tree which is generated after the parser. And you can see it doesn't have like a lot of things here. It types a few things because it knows the types, but a lot of the things are untyped. So this is what's generated after the parser. And then we're invoking the typer, and that's going to go over the entire tree once. And that's the one, like that's the part which is figuring out all these types. Like a few more things. I can generate map files now. Can I? Isn't that just... No, I can't really generate map files. I can probably generate a map file from this. But I don't really know where this is going to be placed. Like, where is this function going to be placed? And if this has like dynamic relocation, I don't know it. I don't know how map files look like if it's dynamic. Like if it supports relocation. Thank you very much for subscribing, Prans.sol. Welcome to the stream. Thank you very much. I really appreciate that. So nice. Cool sounding repo names. I actually love names. I'm really scared because I tend to change my mind very often. That's why I'm like switching themes all the time. So I'm feeling like Luxor is going to be changed, but I also like the name so much, so I think that's actually going to be persistent. The fruit themes. Yeah, maybe. Expression call. So we're going to basically undo, or we're going to basically do what we're undoing here. We're going to place things inside these registers and then just jump. So let's generate a call first. That is expression call. And again, we're not supporting function pointers. So this has to be a primary expression. So we're going to assert, well, you know, this is supposed to be a primary expression. I'm asserting at a different place. This is being catched by the typer, if that's an error. So this expression is a primary expression, which means it has a name. So I'm going to branch to this name. Jump. I'm going to just jump to that label. Name size and name text. So I'm just like writing this jump instruction. So if I'm running the program, you should be able to see jump here. So I'm jumping to test, which is this function here. So what I need to do, I need to place the right things inside the right registers before I'm doing this. And there's one more. And they have to go in the... Because... So this is a problem. This might be... Like each argument to the function might be an expression. So I can't really move the... I have to generate the expression first. And I have to push it on the stack, which means that the first argument is gonna go last on the stack. So eventually I have to place them into these registers in the opposite order. So I'm gonna contain like a loop counter for knowing how many arguments I have. So I'm gonna say argument count is 0. And I'm gonna have a list node. Call arguments. So this is a list of expressions. And I think it's called list node here as well. So I have to process all these expressions, and they're going to be pushed onto the stack. It's a call expression. Yeah. So this is gonna generate something and place it in RAX. So I'm gonna do generate expression here with this expr, and then I'm gonna push the RAX register onto the stack, and then I'm gonna increment the argument counts, and then I can do while argument counts minus minus So let's say I have one argument. Then argument count is going to be 1. Then this is going to start with 0. Yeah, so this is past decrement. So this will work. I can just use the register. Where's the register list? This register list, the index on that list is going to be defined by this argument count. I'm going to place it on the top here. So I'm going to use that as an index. Argument registers of argument count. This gives us the string representation of the register we want to push the thing into. And then we're going to emit no, we're going to pop from the stack into these registers. Pop to RDI. I'm going to make a new function for popping. So this is just going to be pop, and it's going to take in a const char pointer with a register name. One, two, three, four, oh, 5. So I want to print just the name there, and that's it. So the register. Thank you for following, Harmonic. Thank you very much. Yeah, so here I'm really gonna just call pop, and the argument register is gonna be this one, which is a string. So this is popping into what I think is the right registers, and then you emit the call expression. Okay, something is not stack level, isn't right. Are we popping here? I don't think we're popping there. Yeah, the stack level is not right. I'm pushing and I'm popping here. Let's print something. Pop and push. That's the right thing. Just don't know why that fails. It's a generate function, stack level is oh, fuck it. I have this new function. I have to change the stack level here as well. Minus minus, because we're decreasing the stack. We're decrementing the stack, we're incrementing the stack pointer, so we're decrementing the stack index. Segmentation fault, all right. But we're getting something here. So we're jumping to test. Probably the RAX register should be 0. Isn't that telling like how many floating point arguments you're gonna pass in? So before calling this, I should move 0 to RAX. Sometimes Lurk and I enjoy how you code interesting stuff. Some idea what you need to do. Yeah. Jessica Cohen. Thank you very much. Programming has improved. Thank you very much. Like, I feel I'm still learning that very much. Like, after, this is so much more complicated than anything I've done before. And that's the thing which is very cool. I like doing that. Yeah. Happy little bugs. Checks GitHub. Yeah. But that, like, I probably have to do that again. Because when making operating systems, there is so much. I haven't been checking previous projects on like the coding thing, only on like special, like architecture specific things, which I have to go in a datasheet to find, which is very boring. Good evening, Jalbat. Welcome to the stream. Cannot use a debugger. I can use a debugger. I can install Visual Studio or something. I'm probably gonna do that the next time, because I don't like to debug like this. Shouldn't you push all the registers before jumping? I should pop all the registers. I should pop all the expressions into their correct registers. So I think I'm doing it here. I'm popping into RDI and RSI, which is what I'm using here. Can I just try to return here? Jump end lane. I should be able to do like make compile. Segmentation faults. If I think the issue is before this. If I'm just doing it here, I think it should work. We have error 5. So here it's working. I'm pushing racks, this should still work. And then I'm popping RSI and something here. That should also work. So it's a jump test which doesn't work. So I'm pushing base pointer. I'm subtracting 32 from that, and I'm assigning those at the right place. This is probably, I'm doing something wrong here. The RBP. This is minus 24. So I'm basically moving RSI into 24. And then I'm moving, that is an address. This is not right. I'm having some kind of pointer. Why the hell am I generating that pointer? I'm basically using a pointer here. It seems like this is definitely like having some kind of pointer access. It interprets the rax value as a pointer. But the rax value is just supposed to be like a number. So I think we have the issue there. If I jump to end test there, I think it might work. Make compile. Then we have error 5. If I don't do this, segmentation fault. Fuck. Oh, thank you very much for rating, Heroset with a party of 9. Thank you very much. That's very kind of you. What did you do on stream? Is it like some C coding? I think you did C coding before. Isn't that right? Or C++ maybe. But I feel it was C. Thank you very much, Jay Jalbat. We have to figure out why it does this though. This move. So where is that happening in the code? This isn't a load. I think I'm loading things like that. Load from rax. And that is happening if I have an identifier. So if I have an identifier, okay, that's still right because I'm loading the effective address into rax. I should probably be using a debugger. Just go through this. Isn't that supposed to be right? I'm just gonna compile again, real quick. All right. So we're pushing the base pointer, and then we're moving the stack pointer into the base pointer. So this is assigning the stack frame, and we're subtracting 16. I'm replacing the RDI at -4 and the RSI at -16. Thank you for following. That's also correct. And then we're moving the effective address of RSI, which is the second parameter, into rax, and we're loading that address into the rax. And then we're pushing this. Load, load, push. And then we're adding these two and jump to end test, which is RBP into RSP and popping RBP in and returning. I think that should be right. Maybe this is not working. I feel like maybe I'm not assigning all the things I should be assigning. This is no parameters, only one, which is a U64. Which is this plus this, and return the data. So I have only one argument there, but it's still aligning to 16, which is correct. And I'm moving 5 into rax, pushing rax. 5 into rax, pushing rax again. Yeah, so this is actually pushing the arguments. And then I'm moving 5 interacts again. This is a stupid way of debugging. I guess I'm first taking the right hand side. So this is actually down here. This is for the left hand side. No, right hand side. And then I'm doing this, which is the left hand side. And then I'm popping both into RSI and RDI. And jumping to test. Wait a second, should it be call? Shouldn't it be call test? Fuck. Is it really possible? This is not a jump. Fuck me. This is a call, the base point, like, you can't return. I'm so stupid. It is gonna return to the caller of this main function and the stack will be corrupted. Great. And error 15, and it's working. That's finally it's working. So we have an error 15 because we're compiling that basically. We're compiling that. That is so cool. So let's see if I can have multiple parameters. C, which is a U64, A, B, C, and we have 3 more. D, E, A, B, C, D, E, F. So we're just adding all these together. So I'm gonna say 5 times 6 plus this is 35. That's supposed to be 35. And we have error 35. That's perfect. That's great. Okay, so we can actually compile function calls now. That's great. I want to do strings as well, so I want to do printing. Because I'm actually linking this together with a standard library. So I should be able to call print. If I'm just having the right label. So then I probably have to turn off this this declaration checking. So I want to have like I want to be able to do hello. Because we have this call, we just have to support strings. So this is a primary expression. So we're going to support this one now. Thank God this is working. RSI is not even used. Add different numbers. We can actually do something more cool. How do I code like factorial? Factorial takes in a number and it returns a number. So you're gonna check if the recursion is working. So this is really gonna compute number times factorial. Is it multiplication or is it addition? Is it like number times number minus 1 times number minus 2? I think it's times. So we want to do if number, we don't have if statements. We have to implement if first. So we can't really do it. But we can test this though. But it should work, recursion should work. So this will be like 15, 21. Error 1. I'm doing this. 21. Okay, perfect. Is it 1 times 2? Okay, nice. Fibonacci. I was actually gonna do Fibonacci, but I think What is it called? Factorial or simpler. I don't know if it's called factorial. I think it is. Let's support strings. I think I have to add string support in Elixir first. So we're adding token number. We're gonna add string. Yeah, string. And we also need to handle, because I'm writing here, I'm writing this new line. Let's go back. I'm writing this new line. So we have to support this kind of expression. Yeah, okay. So we're going in the Elixir, we're diving into the Elixir. So let's start in the main function. Process the next token. If this is a number, I'm gonna do parse number. Else if C, I think I have to do, I can just do this. If this is a starting code, I'm gonna parse a string. All right, so it's currently pointing to the opening quote, and I'm just going to ignore the quote because the quotes aren't really needed in the. This is not represented with the quotes, so I'm going to just use this part. I'm actually just going to ignore this. I'm going to wait for this ending quote. So I'm saying token name text is equal to Elixir cursor. This is telling where it starts. I'm actually going to advance Elixir first. Now I'm just going to skip it, because you can't really, you're not supposed to skip white spaces inside a string. So yeah, I'm just going to manually move it. Yeah, I'm going to take advanced Elixir, because this will only skip the current one. It will be skipped to whatever this is. I think maybe that's not the right way. I'm gonna do it now. I'm gonna make a new function for getting a char, which I'm gonna use another place as well. I'm gonna just increase it manually, I guess. Elixir cursor plus plus. So while Elixir cursor of 0 is not equal to the quote, I'm just gonna advance this Elixir pointer. We kind of need Elixir. If this goes over in a new line. I'm gonna have to think about what we're gonna support. Anyway, if this is returning, we are supposed to have this quote. And we should also check for the 0. and Elixir all right. I'm gonna say if Elixir cursor of 0 equals the quote. If it doesn't equal the quote, if it's equal to 0, we're gonna have like an error. Error on some kind of token. So I'm just gonna exit with some kind of code here. And then I'm gonna skip this last quote. We're gonna assume everything is happening on the same line now. Before I'm skipping it though, I'm gonna assign the token size. Let's do Elixir. Cursor minus token name text. So I'm taking the new position minus the previous position. And this might be -1 because we're skipping this quote here as well. And we're gonna set the token type. Token string. And I think that's it. So if I go into the parser, and this will be an expression. So this will happen in expression parser. Down here. Actually, let's print the string. It's equal to token name. It's handling, okay, so it's missing that one. That's fine. Just catching that one. So we've got a string, and we're missing the last thing here. So I guess the first one is, yeah, so if it's currently pointing here, I guess it's right to take just the size, not -1 there. So I'm gonna disable this -1. What? What? There we go. So got a string. So this is the actual string. And the primary kind failed. And that's because we're not setting the kind here. So if the token is a string, I'm gonna have to update this primary token. And we don't have a string here, so we're gonna add a string first. So we have a primary expression here. So I'm gonna add, this is either some kind of identifier or it's a number. Or it's a string. I'm using the same name here, that's probably not allowed. It is not. I'm gonna just call it string. And we're gonna say that string equals token name. We're gonna delete this. And kind equal primary string. I'm gonna add a primary string type. String. Okay. String size. The string size is actually encapsulated into this string object. So we have the string size. Yeah, I don't end there. That's correct. So we're gonna have to go back and fix that one. So this is generating an expression. And if this is a string, it's supposed to be a char pointer. So I'm gonna assign it to type char pointer. This is supposed to have a type here. Primary type. I'm not gonna assign it there. I'm gonna assign it in the typer instead. So when the typer goes through, it's gonna check all the primary expressions. I'm probably gonna use separate functions for all these cases. So if this is a primary string, we're gonna say the expression type is equal to pointer to a pointer to a char. So this is a new type. Actually, I'm gonna say new pointer. New pointer. So the type is being set there. And I'm gonna say type pointer to is equal to type char. And then we're setting the expression type equal to the type, which is this. So that should handle the type for the strings. So if I'm gonna generate, let's just see if it works first. It says a primary is not handled. What are you talking about? Primary not handled. I guess that's in the printer. So I have to fix it in the printer as well. So if this is a primary string, we're gonna load the string first. Name is equal to primary. Don't do that. Let's just do this. Indented print. This is a string. And text. So now we get the argument is a string hello. And then we're complaining about this, and we have to change this. It is basically looking up the function, and this is an external one. So eventually we'll have like system calls for this, and that'll be defined in some file, some standard library or something. So this will actually be defined. But now we're just testing stuff, so it's great to have print before everything is working correctly. So I'm just going to disable that statement. I think that's in the typer. So whenever we have a call, we're checking if the declaration exists. I'm going to do else here. Expression type. So we're going to disable that error. It might be that we don't know the return type of this. So we might just set the return type to nothing. And we're having like primary expression are not handled. I think that is in the generator. So in the generator, yeah, in the generator, we should handle the string here as well. This is very messy. I'm gonna I want to have a separate function for it. I'm gonna fix this later with the other things, but let me just make a function for the unary, not the primary expression. Okay, so if it's a primary expression, we're going to generate that. So we have to support strings here as well. If primary, if that is a primary string, we're going to emit like a data section, I think it's called, and we have like the symbol ASCII 0. String AT&T x86. ASCII. It just says string here. And it's load. How do you load this one? That's string number 1. Where are you loading that? Okay, so move string number 1 to ESI. Is that going to load the address? I think that's going to load the address. How to level? Move SB. Okay. So it's just terminating with a null byte. Okay, for with a null byte. So I'm having a label, and we're gonna say string, and how do you access those things? Let's just try using that syntax there. And I'm gonna try with a move instruction, or just a load effective address. Maybe the ARM syntax is like ASCII. So we're gonna emit data. This is gonna be placed like in the middle of the code. I want to place this at the very end. If I want to place this at the very end, I have to place this in a buffer or something. And since I don't know how big this is going to be, that has to be like a dynamic array. There isn't really another way of doing this. Okay. Let's just try to do this. And we're going to emit it right into the code. 1, 2, 3, no, we're gonna have a label first. So we need a unique label. So I'm gonna just have like string, and we're gonna give the string a number. And a semicolon. And this is gonna be the string index, or this, like, the string number. I'm gonna have a string number here, and that's gonna be a static string number inside this function. I can probably place it here. String number plus plus. So we're giving it a unique string number, and because we're just going to call it here, and this has, of course, to be we have to replace this later. Okay, so that's the label. I'm going to give it a string, and we're going to place the actual string here. Which is the primary string size, primary string text. So if I'm doing that correctly, we should be getting something more in the outputs. We should be getting string number 0, and we have a string hello, and this has to be in quotes, I think. Yeah, it has to be in quotes. So I'm gonna escape the quotes. There we go. So we have a string, and not only do we have to use a string, we have to make sure the address of the string is placed into RAX. So after this, or before this, I think it doesn't matter. We're gonna load the effective address of this label. Let's do string number plus plus down here. Of this label into RAX. So we're loading it in there, and we're loading the address of this string into RAX. Hello. There we go. There we go. There it is. It prints hello. Okay, I think this is gonna be good. Find push pop. Oops. I didn't mean to do that. And there we go. So we're gonna disable the assignment printing. So when we set up the stack frame, I'm gonna remove the printing from there. So this is the actual program, and we're generating error code 27. And that is because we don't return anything from the function. So I should be able to print whatever data is. So like data is equal to, and a new line. Let's just print data here. So I'm actually printing the value of data, and I'm returning 0. And there we go. 27, isn't that right? 21, no. This is 5. No, it is not right. The data is corrupted here. Data is equal to 27. Replacing all these. This is only calling 6 arguments, like the 6th argument will be wrong. So this is taking in 6 arguments. So this will actually add something which is not, probably 5. So we're going to consider this. So this is 10, 15, 21, 26. And it's given 26. That's so cool. That is so fucking cool. So we can print. That's great. Yeah, missing one argument in test. That's right. This is good. I want to check if recursion are working, so I want to have some kind of if statement. So I want to add if statements. And I'm thinking I don't want to do this C shit where you have to do parentheses around every single thing. I think you should be able to say like data equal to 26. And we're gonna have like else if. Oops. And else. So I want to implement this here. And we already have this. So we can already do this comparison. And remember, like this is just an expression. So this evaluates to a number, which is placed into RAX. So I can say like data here. And this is just gonna go in, it's gonna fetch the address of the data, and it's gonna load that value into RAX. So we're basically we're gonna compare and check if RAX is equal to 0. And if I have an equal, for example, 45 equals 45, this is going to be 1 if they're equal, or it's going to be 0. So I just have to compare and check if the value in RAX is non-zero. And then I have to branch. Yeah, okay, so we're gonna implement this very simple. This is actually really simple to implement. So we're gonna implement this like, we're not gonna consider the else if. This can be rewritten as 45 equals 45. If this is true, do something else, do something else. This is the only thing we're gonna implement. And if I want to have else if, that's gonna be a new if statement inside this else block. So then I can check if data equals 45, do something there, and then else. So this block here will be the same as this block there. So we're gonna make some kind of parser function, which is gonna check if we have an if, and then it's gonna parse the else block as a new if block. And this is optional, so we can have it like that. It's gonna be either it's gonna be an else, or it's gonna be an else. So either we have an opening curly or we have an if keyword. Yeah, okay. Let me take some more water first. I'll be back in like 2 seconds. All right. Actually, let's implement everything. Let's implement for loops, while loops, if statements, all in one go. So I want to say like while is going to be like this, and we have a for loop like, a for loop can also contain a declaration. So this is really just an init statement for that specific loop body. So we can, no. Or yeah, we can actually do it the same way the functions. So I think I'm gonna do it the same way. I'm gonna just open a new scope. That's gonna make the code a little bit cleaner. We can't possibly, since this is only one thing, I don't know, we can possibly do it the same way. So I want to have like, I want to declare I is equal to u32 is equal to some value, optional value, and have a condition here. Like this. We can either do the rest style for I in like this, but then we have to use type inference on this I, because this is going to have the type of this. So if I can make type inference work on really simple examples, I can implement that one. So let's see, where is the type inference in the code? Like, how far is that gonna go? So type inference, that is a declaration which doesn't have a type. So this happens in the declaration stage where we go through the scope. So it happens when we resolve the type. If this is pointer, if it's unknown, else we're gonna have inferred. Inferred type is not really something we can resolve. And this doesn't have like you can't have a pointer to an inferred type. You can't declare something which is a pointer to something inferred. That doesn't make sense. So in other words, if we have an inferred type, we only have that inferred type. Type function. Resolve type. So you're gonna check here if the declaration type kind equals to type inferred. If that is inferred, we're gonna check what that is equal, because then we should have an equal expression. So I think I'm gonna add, I need to add the init expression here. The declaration needs to know what is supposed to be equal in case of an inferred statement. Who? Hello, Savage Marcus. Welcome to the stream. So this is a type. We have an inferred type. The only thing which we're storing about the inferred type is that it's an inferred type. We don't store anything. Yeah, this is really a declaration as well. I think I can go into the declaration, and this is going to have a pointer to the init expression, if it has some kind of init expression. Yeah. So just for now, we're going to make a pointer to the init expression. So if this is something, it's supposed to be initialized with some value. So we're going to be looking at the case where we have an init expression and a type kind is inferred. So I'm gonna just fix this pointer first. So that'll be in the declaration parser. We're parsing the init expression down here in case of an assign. So the init statement, this is actually a statement. That is actually a statement. which is gonna be resolved by something. I can actually use the init expression here, and this I can only set this to the assign right. So I'm gonna set it to the assign right if I want. I can also set it to the just the statement. I don't know what's best. I'm gonna say declaration init expression is equal to assign right. So basically when you have like an init, data is a u32, which is equal to some expression here. Then this is equal to data is a u32, and data is equal to 345 plus 234. So I'm basically constructing two expressions out of this one. And now I'm just saying that this declaration here, which I'm making here, that is supposed to point to the right-hand side of this assignment. So I know what this infer type is supposed to be. That is one way. Or I can actually make the pointer in the actual type. I don't know what's best. I'm gonna just do it like this. Yeah. So I have to be able to know that expression on compile time. And I can't really do multiple passes at this stage. So I'm gonna see, let's make an infer statement. Data is equal to some value. Then we need to know the value of this guy here. Do we really need to do this? Because this assignment is just gonna go on the scope. So this is really just being data is equal to 45. And then we can look up data. All right, I'm gonna do it differently instead. I'm gonna delete what I just did. We're gonna delete that. I'm gonna delete that. And instead we're just gonna track if we have an assignment. And one of the nodes is an inferred, has an inferred type. Like this. So in the typer, if this is a binary, I'm typing a binary expression up here. So I'm typing the expression for both. For the right first and then the left. So the right should have a type now, which means if we have to figure out if this is an type expression left. We can also mark expressions that in it. That's gonna make it simpler to do this. I'm gonna make an if. So if binary kind equal no. If binary left, let's look at the left hand side first, which is data. If binary left equals expression primary and binary left primary. Is that a pointer? No. Is a primary identifier? I'm just gonna have it on next line here. And and the primary declaration, which should be available now, if the declaration type kind equals type inferred. Oops. I'm just going to print got an inferred type. Okay, I'm missing a new pointer. Initialization, okay, so 181 is supposed to be a pointer in typer. 181. This returns a pointer. We can actually make this return just a void, I think. Doesn't really matter. So we're typing the program. We have this kind of thing. We're typing the right first. Got an inferred type. Assert binary left. So this is something. If that is a primary, do we have the tree? Because we have a declaration data which is inferred. That is right. We also have data equal to 45. So this is the one I'm trying to type now. I'm trying to give data type based on this number. I just don't know why I'm getting a seg fault. I should at least print that thing. Getting an inferred type or something. Typing the program. Okay, I'm doing something in a typer, which is not right. Let's just use data here. We still have a seg fault. It doesn't make any sense. Okay, did we do something here? Okay, so there is an issue with this function. If that is expression primary, then we can check the primary kind is identifier, and this might not be true. So I just want to see if it goes there. And we have, okay. So this is the thing which is having the error. So I don't think it has a declaration. So you're going to assert that this binary left primary has a declaration. Okay, so it doesn't have a declaration. The thing which is happening is that when we're typing binary left, this is a primary, so this doesn't have a declaration. We're supposed to fill in a declaration for this identifier. So if we're saying data is equal to something, I'm going to fill in a declaration for this identifier. So whenever that is probably happening here. You know, I think that might be happening there. If I move this up, then it's gonna work. So let's try with a inferred type error. So now that you can see that it's working. It is actually typing unsigned 8 bytes here with the data. So now data is unsigned 8 bytes. The problem is that data should be changed here as well. I shouldn't only do this. I'm getting an infer type. Wait a second. I'm not getting an infer type. I'm looking up some stuff here. Let's use a different name. So now we got an infer type. It was probably just using the same, I don't know the direction it checks thing when it pushes things on the scope. This should be like an error if we were using the same variable. And that's very easy to fix. We're gonna remember to fix that. But now, it says that test is an infer type, which is right. And this is inferred. So the only thing we have to do, we're gonna still assert this part. We're gonna assert binary right type. So the right hand side has a type. And then we're going to just assign that type to the left hand side. So binary left. So the actual binary left. Yeah, the typing is actually happening here. So we're just going to assign this type. This type is going to be assigned. So that's inferring the type of the right. And yeah, because this is actually accessing the declaration. This is a pointer. So this will make sure both this one and this one gets changed. And it gets. So we have an inferred type there. But this one gets changed. So I don't know why this variable identifier doesn't have a correct type. Primary declaration type. So I guess that the binary left. Okay, we might just assign both of them to the correct value. Binary left. I just want to make simple type inference work because it's going to make the loop simpler. And this is also right. So now this is working. Let's see if I can do something more complex. I'm having like data, which is a pointer to something, referring to the token. And I'm gonna assign test equal to the value pointed to by data, which is supposed to be just the array of so many tokens. Yeah, that doesn't work. Wrong symbol there. It doesn't know the type. Okay, so this is correct because it doesn't know the type here. I'm gonna change this to something known. So now the data is declared as this. Yeah, this is gonna work. This doesn't work. we have to propagate the type for unit expressions as well. So this is going to work. So now declaration data is no test. That is just an unsigned. What the fuck? Oh, data is declared as. I'm using the same variables over and over again. I'm gonna check that right away. So we cannot use same variables which we have used before. Is something like this possible? Like in Rust? I don't know. It is not going to be supported yet. Probably later. Will you write a linker? Yeah, I'll write a linker. I'm going to be able to, like, I want the linker script to be able to be typed in the program itself. So you should be able to write normal code, just call into a few compiler functions and write the linker yourself. I don't want to have like some standard linker scripts. The only command you will ever write in this language is luxury build.lux. It doesn't have any commandlet arguments. This is the only thing you're gonna write. I think that's clean. Do you like VSL? Like, how do you like VSL? I think it's good. Might be a little bit slow sometimes, but it's fine. Or maybe the terminal is slow. I'm using Windows terminal. It looks a little bit better, but it's horribly slow. So satisfying. Thank you very much. It's a cherry red, I think. Cherry red switches. And that will build the whole thing. Yeah. I want to have one single file in the language itself, and that's going to build the entire thing. No makefiles. Just call one program. Yeah, so when I'm parsing this, I have to make sure every new element is unique. Every new declaration is unique. Thank you for following. Thank you very much. So we have one function which is called push declaration on the scope. And this should really make sure that the declaration doesn't exist already. So I'm going to be doing something similar as in a typer, where we have to recurse up all these parent scopes. So declaration okay, so before I can push it here, I have to check if it's already defined. Thank you for following. Welcome to the stream. So I'm gonna, yeah, I have to do this again. So this is gonna find me a list, and this will work. The reason I have to do it here as well is because I'm recursing. So I have to compute this new list interface each single time. So now I know the list. Now I can just say list node iterate. We're gonna iterate this list, and this is a declaration. And I'm going to compare the names. So I'm going to compare the declaration name with this declaration name. So if string compare, this is a valid function. It is just colliding with the names provided by GCC. So if declaration name, I need a pointer, is equal to new declaration name. Does declaration exist? And it's going to return a Boolean value. So true. See, if the declaration exists, is going to return true. And then we're going to have the case where the scope has a parent. So if the scope has a parent scope, I'm going to recurse into that as well. With the same declaration, but now I'm going to go into the parent scope. I'm actually going to return here. And if the last case doesn't have a parent scope, it's going to return false, and then recursing up again. So I was going to check if it's on the scope already. Actually, I'm gonna return a declaration from here. So I'm gonna return a new declaration if it's already found. New. Return new declaration. And return 0. So I'm gonna call in, before I'm adding it to the list, I'm gonna call this one with this declaration and this scope. And if that one is something, I can probably say if so if declaration existing declaration equals this. Is this allowed? I don't know. I have to see if this is allowed. If that is true, we're gonna print an error. Error token. This is also gonna give us information about where it's defined. But I'm not gonna use that because I don't have an error function which can take that in as an argument. So I'm just gonna report this declaration name token. Declaration is existing. Let's see if that works. No, that doesn't work. I'm just going to see if that returns something. So we have declaration is existing. So this one is already existing and it's up here. So I have to say like, give it a different name. And then it is actually inferring this correctly, I think. Yeah. So test is going to have the size type of array, which is this. Yeah, so that's working correctly. And if I also want this to work, like the deref, that is really going to return just this part, not the pointer. And this doesn't work, and that's because it's not propagating correctly. Type unary. I'm looking for type unary here. So expression type. So this is really going to fill in the expression type. That is what I'm looking for. And it says error 86. This is generate restarting. I think, oh, it's working. Oh, it's working. Yeah, is because this is already filling in the values. I don't know why it didn't work, like last time. Probably because it was a duplicate declaration. So now simple type inference work. Thank you for following. Welcome. So now I should be able to do like for I is equal to 0 to 5. This is going to go from 0 to and including 5. And then I have, like, I don't know, maybe you don't know it. Like, how is this done in Rust? Like, what is, because I assume you can do this in Rust, what if I is already declared before? Is this going to declare it again in a new scope? Is this going to be like a new declaration in a new scope? So for example, if I had an I, which is equal to 5, and I want to use this as an iterator, I can't use that using, like I can't do that using this syntax here. This will be using a new I, correct? Oh, thank you for the subscribe, Redina. Welcome to the stream. Thank you so much. I really appreciate that. And that will build, yeah. VSL is so cool and useful. Yeah, it is. It'll shadow. Okay. So I guess that makes sense. So we want to make support for, okay, this is going to be what we're going to support or implement now. We're going to implement for I in some kind of range. This might be like, this might be whatever you want. It can be like an expression here. That doesn't matter. It might be even plus. It might be a function call there, like whatever, doesn't matter. So we want to implement that. We want to implement while loops. While loops, which is just like while this is not equal to 0, do something. We want if and else. Yeah. We're gonna start by implementing those things, I think. And like, how many loops do you have in C? Is it only for and while? You have do while as well. You have for while, do while. Because the only thing which is different here is that this is gonna have a pause expression. So we need to know, maybe this is gonna be like represented as the same kind of structure. I think I maybe want to do that. I'm going to implement this the same way as this. This is going to have the same structure. And then I'm going to implement if else as a separate thing. So the first thing we need to do here, we have to add support for a few more keywords. So we need for, while, if and else. This not equal. We have equal, do we have not equal? We should be having not equal here as well. So I'm going to be adding not equal because that's very nice to have. And we're going to be adding like a double dot for like the range. So I have to add like a few more keywords, and we have to add this one and this one. And then we're going to be able to implement it. Okay. Our outputting, yeah, it's outputting ASM. Else branch for statement in case of 0 iterations. Switch. Yeah, switch loop, no switch statement. And we're not gonna add switch statement. They require a little bit more fuzz. This is very simple to implement. I'm gonna go to the toilet and then I'm gonna be back in like 1 minute. Let me continue then. Bitwise. For each. Isn't this the same as for each? It's just a different name. For iterator in list should work. Yeah, I totally agree. But that's gonna require to know what the iterator is. Bitwise operators are expressions, not statement. Yeah, that's correct. Yeah, we have to add it to the tokens. Yeah, let's add those two first. So I'm going to start with not equal. This is not equal. And like down here, I think we're going to have double dots. And then it makes sense to have dot as well. Dots. They're really just the same thing. Almost the same thing. Yeah, I'm gonna add it under the comma. So case dot. And then we have, I don't know if we have it already. I don't think so. Yeah, because I'm gonna have like an exclamation mark. So if that one is dot, and if the next one also is dot, we're gonna say this is a double dot. Otherwise, this is just a dot. And this needs to be 2 though. So 2 symbols there. And if the first one is an exclamation mark, and the second one is an equal, then we're gonna say this is a not equal. And 2 symbols. So now we should be able to recognize like this and this as well. And for the keywords, we're going to implement a few unique keywords. We're going to implement for, while, and if, and else. So those are the new keywords. And we're going to add them here as well, so we can actually access those. I have to get the right order. So for, while, if, else. For, while, if, else. So those are the keywords. I think, oh, in, we need in. Keyword in. Is that at the very end? Yeah. So keyword in. Unicode support. I'm not gonna focus on that. That's very simple to add though. That's just a lecture. It can be replaced like at any time. Emojis. Animated GIF. That's a nice feature to add later. Okay, so now we're gonna actually parse those. So these are not gonna return anything. These are not evaluating to, like if we're gonna have the ternary operator, probably, but that's gonna have a different syntax. We're not gonna care about that in the beginning. So these are statements, they're not gonna return anything. So I'm gonna go into the tree. I'm gonna make 2 new nodes. for the statements. Where is that? Here we go. So I'm not sure what I'm gonna call it. I think I'm gonna do like loop. So loop statement and conditional statements. Yeah, let's start with that. So I'm gonna say just loop and conditional. And this I'm gonna copy because loop is much simpler to write. We're gonna call them here. And both is gonna have an entry in the statement main statement structure. And conditional. All right, and then we're gonna make two more enum values for the statements. Conditional. Okay, so now we have two. We have loop and conditional. They should be enough. Do while. I'm not gonna start with that. They're basically the same though. We can implement that as well. Do while. It is just kind of the check at the very end instead. So that would probably be cleaner if we had a different statement for that. Because that's kind of different. Or you can make a tag which is telling like, is the conditions gonna go at the front or the end? Yeah. We're gonna start with this. Goto, no thank you. We're gonna add defer. That's gonna basically eliminate the use of goto. Okay, parser. So this is a statement. So we have to go to the main statement parser, which is here. So this is parsing like the top level statements. So we're gonna add entries for return. We're gonna add two more. Actually, we're gonna add three more. Yeah, three more. So you're gonna check if this token is a keyword for. So this is gonna be a for loop. That's gonna be a for loop, and then we're gonna have like while. And if. The else keyword is going to be parsed from inside this else if, because it's basically a new else statement, which can only be an else. So, thank you very much for following. Welcome to the stream. Yeah, let's make functions for this. So these are just parsed inside there. I can actually I need a separate function for this one because I need to parse this again in the else case. So for this is not really that important. But maybe I'm gonna do it on all. At least this if I have to make a separate function for it. That's much cleaner. So this is parsing an if. Let's use multiple functions there. One function per statement. Parser, thank you for following. Everybody, welcome to the stream. Parse, do we have like 4 statements? Yeah, so that's going to return a new if statement. We don't have if yet. We have to make sure we know what these are actually going to do. So the loop expression might have, it's going to have a few pointers. We need to know, what is supposed to be done first. So this is going to be interpreted as like I inferred 0. As long as I is less or equal to data, then I++. Yeah, I don't know what Rust is doing if it's like, if data is less than 0. I think this also, like always, is supposed to increment I. So we need an expression for this past operation, and we need a condition, and we need some kind of declaration. And then we need a body, of course. So we can start with the body. The body is just a new statement. So a statement might also be a compound statement, which in this case is going to be. And then we have a past statement. That's the I++, which can also be like I. This is for loops. We're going to be doing this. So we only need to have, maybe we're going to be doing like, maybe we add a new one for just a for loop. We need to know these two limits here. I just consider where we're gonna make this logic work. Is this gonna be done in the generator or the parser? We might need very much for this actually. Okay, I'm just gonna do it in the parser. So then this statement here will be the past statement. And then this also might work for loops, general, like this. We can just change the code, like a keyword name. And then we need an expression here, which is just an expression. Condition. And some init expression. Yeah, so this is what we know. It's going to be an init expression. Init statement. Something like this. I don't know. Something like this. Conditional is going to have like an expression condition, and it's going to have a statement true body and a statement false body. All right, that's the only thing it's going to have. And then this statement here might also be a conditional statement again. Conditional. I don't know if that makes sense, like the words I'm using. I hope so. So we should be able to call these keywords. And we have to remember, no, we're not doing next token there. We have to skip the token first. We skip it here. Okay, we're not gonna skip it. We're gonna skip it inside these functions. So this will call parse parse for statement with the parser actually return parser and parse if statements. Parse for statement. Yeah. So let's start with the for loop. I'm gonna comment here how that's supposed to look like. For I in some kind of range, where the range has to be like defined before, because this is inferring. So that applies some adds some restrictions to where those variables can be defined. So ideally, if I do like data to 5, this should work, assuming that data has been declared before. And that's because we don't, like when we're inferring stuff, that's kind of in the wrong order. So that requires a second pass. I have to go into how type defs actually know how type inference actually work, because I don't know that. The problem, like, oops, yeah. The problem is that if you declare like A should be equal to B, then the type inference needs to know what B is. And B is defined down here to be equal to C. And C is defined to be equal to 5. So this don't work because it doesn't know what B is. This don't work. And here it can type what C is. So this is inferring that C is going to be like int, for example. And then on the next pass, it has to go up here and figure out that now B is equal to C, which is an int, which is then int. And on the third pass, then A is equal to int as well. So this requires 3 passes. But maybe you can do like some linked lists implementations where you build some kind of data structures for knowing, like, if you resolve one thing, what can you then resolve after? I don't know how type inference actually work. I've heard there are some cool algorithms for doing that, but I don't know exactly what they are. The only thing I know is that I don't want to do like lambda calculus and stuff like that. I really hope I'm gonna be able to avoid that. Anyway, so that's the reason why we have to declare those variables first, if those are identifiers. A match statement, like in Rust, like I don't know how the match statement is in Rust work. Algebraic data types like Rust ones. I don't think so because I don't know what they are. I'm gonna take a look at it though. Step option for statements. Maybe add a step option for statement which defaults to 1. Like step instead of continue? Or what do you mean? I don't run the unit test. I'm gonna... No, not at the moment. Shouldn't false body be a conditional? No, not really. Like, yeah. It might be. Like a false body might either be a conditional or it might be a statement. But as you see here, the conditional are inside the statement. So this might either be a conditional again, or just a statement. So you're totally correct. This might also be a conditional. No on every iteration. Step. I didn't understand the step keyword. Parser looking good so far. Thank you very much. It's not looking like I have to clean up a huge, like a lot. Not a huge. What am I talking about? So we're currently just pointing to the 4. So we're gonna skip the current token. So we're going to skip the current token. That should give us I. And this has to be an identifier. And that's going to go on the scope. We'll have to open a new scope for that. Or should we open a new scope for that? We have to think about that. Anyway, we want the next token. So I'm going to save this in a token variable. So now token is supposed to point to this identifier. Actually, this can be a like expect identifier. We're gonna expect token identifier. That is supposed to be the next one. So that's the token. This isn't really an inferred declaration, so I have to make a fake declaration and push it on the scope. And declaration is equal to new declaration. And declaration kind. We're going to say variable declaration on that. And declaration name token is equal to new token from this token. Are we going to, oops. We're going to store this token, which is the I, inside this name token. And then we're going to save the name as well, just for faster access. And we need a mapping, so we need a type here. So we're just going to do new type and make it inferred. And then the typer is going to fix the rest. So I think this is a good declaration. We're also going to make a new conditional statement. Which I'm thinking like this is just a statement. Okay, so we don't need to make a new like function for allocating that. We can just do like loop. Loop is equal to new statement loop. And then we can say loop. Well, yeah, this is only going on the scope. So we have to push this here on the current scope. Push declaration on current scope. And we can also push on the scope. So I might actually parse this compound statement. Like, so this is what's happening. When I'm parsing this is a new compound statement. This is going to return a new compound statement, which is going to have a pointer to the scope. So I can parse this first, then I know what scope this is, and then I can push this declaration on the scope. But if there's an error there, I will have like this being the duplicate declaration, which is a little bit weird. but it's probably fine. Thank you for following. So I'm gonna ignore, I'm just gonna save this declaration here. I'm not gonna do anything with it right now. And then we need to skip this in, so it's currently pointing to I. And we need to move the pointer first, and then we need to skip the in. Yeah, it doesn't really matter how we do it. So I'm gonna say next token from the Lexer, and then I'm gonna skip token. And this is supposed to be, this is not really gonna skip a token, this is gonna skip a keyword. So I probably want to make a function for expecting a keyword. We will have if is keyword. I want to have like it's gonna return a function, it's gonna skip a keyword. Take in a token, no, take in a Lexer, and taking a keyword kind. Thank you for following, guys. It's very nice of you. Skip keyword. We're first going to get the current token. So this is the current one. And we're going to assert that that has a type kind. So if is keyword token kind, if that is false, I'm gonna error token keyword is wrong. I think I have like expecting some, this is just a token kind. I probably should say what I'm expecting, but I'm just gonna do this for now. It is very easy to fix though. And I'm gonna return next token. So it's gonna skip the keyword. So now I should be able to do, oops. Skip keyword. And the keyword kind is keyword in. So that is just skipping the in keyword. So then we know that the pointer is, like the Lexer is pointing here. And this can either be just a 0 or it can be an expression. So this, I'm gonna parse the first expression here. So I'm gonna say a loop. This is the init statement, actually. No, it's not. This is a this is gonna be, I have to make a new equal, like an assign node. So I'm gonna assign I to 0. So I need a new primary expression for I and a new primary expression for 0. And I don't want to do that. I want to make functions for doing this for me. So I'm gonna say I'm gonna make a new statement. This is gonna be a new is this already a function? I think this is already being declared somewhere. New assign. I don't really want to call it the same thing as this because it can cause confusion. I want to call it like, it is really a new assign, but it has some parameters as well. I'm just gonna call it like this. It's fine. I'm gonna figure out a cool way of doing this without having too many name collisions. But we're gonna just do it manually. So this is the name is equal to new primary identifier. Name is equal to declaration name. And name declaration, we don't know the declaration yet. Actually we do. We can just fill it in. But it doesn't matter. We can probably fill it in. I'm gonna fill it in here, because otherwise that's gonna be an edge case. Okay, so name and declaration, that's all we need for an identifier. And then we have the number. I probably want to make a function for just returning a number. There's going to be some refactoring here, for sure. This doesn't need to be a number, this is an expression. So I just need a binary between this one and this one. And then we need a conditional between this one and this one. Actually, maybe I'm not going to implement while loops right now. But I'm going to implement if else. So I'm going to ignore while loops. I want to make it cleaner. I want to make it a little bit cleaner first. So the primary number, I'm not going to have a primary number. I'm going to have a binary assign. So this is a new expression. Expression binary. I thought I had a new binary function. New binary. Binary assign. And then we have the operator. We don't have any operator. So I'm just going to point this to the declaration token or something. Name token. And the left-hand side is going to be the name. We need a cast here. And the right-hand side is going to be parse expression. All right. Why is this not highlighted? Okay, so that's supposed to track this first one. So the init statement will be, that's a statement. So we're gonna just assign it to the, fuck, why don't you have an expression statement of this? Dang it. And then we have to give it that one. Expression statement. I don't want to do it like this. This is so stupid. Because I'm making this node myself and linking them together. That's really dumb. Yeah. So the init statement is going to be just an expression statement, which is an expression, which is this assign. And we have the name, which is the identifier. So we need to make a conditional It would have been great to like have that as an input there. Like statements, and that takes in the expression as well. But then I need to, I don't know. Can probably make a function of that. It's so stupid when some functions are taking in stuff and the rest doesn't. I'm just gonna do it like this. So we're gonna have binary less than. This is a binary. Less equal. Less equal. And the operator is equal to declaration name token. Left is equal to, that's primary name. The right hand side is equal to parse expression. Parser so that's the assign. No, that's the less equal. This is parsing a new expression though, so we need to make sure to skip the double dot first. Skip token. Double dots. And then we parse the new expression, and that's basically it. So then I can fill in the rest of the loop expressions here. So loop condition. This is not an expression. That is an expression. So I'm binary as an expression. I don't need a new statement here. I can just set this equal to the less equal. Loop condition, loop init statements. So we need the pass statement, which is equal to this increment thing, and we need the body. So the loop body, that will be simple. That is just parse compound statements. And then we need to make this increment thing. Right now we have for I in 110 without being able to define how much to increment the iterator by. Yes, so it's only incremented by 1. Oh, was that a step option? Okay, I understand now. The step option. Okay, I understand. That's a nice feature. How should that gonna be like? Step is equal to 2. I don't know how it's being done in Rust. Kinda is a little bad syntax there. Good evening, Paranog. It is a new language, yeah. I'm compiling into x86 assembly. I'm planning to use LLVM if I want to have greater speed, but not currently. Like, I'm not really interested in the speed. I'm interested in just the coding, to be honest. Yeah. When I'm writing an OS in this language, and a few things for the new chip I'm planning to work with, if I'm then gonna do some game, which I really wanna get into how to do that, I might do an LLVM backend, because then you might need more speed. But I don't know how much slower this is gonna be. if I'm at a register allocator on this, I don't know how many times slower this is going to be. Did you learn how to make a compiler at the university? We have a subject. I'm taking a subject on this year, but I'm not learning it there. Not at all. My computer science degree was actually a lot higher level than C-level programming. Yeah, they usually they never really use C anymore. It's like Python and C++, and we haven't really had any experience with low-level programming. Like very little. Which is a little bit stupid. Yeah, this is tricky. This is tricky. Binary. I'm gonna call it post. New binary. Binary add. Or plus. So this is gonna be +1. And do I have a 1 somewhere? No. New binary plus. I'm actually going to sign this up here. So this is a sign. That's being assigned here. I can reuse this assign token, by the way. So I'm going to use a plus here. Binary assign. No, I can. This is defined before. New binary. New binary assign. I'm gonna remake this. So make a new binary, which is assign. We have to do the plus first. So I'm gonna call this 1. New primary number 1 token. I'm gonna say it's equal to declaration token. 1 number is equal to 1. And then we can say assign left. That's assign. Okay, so we're allocating a primary, that's a number 1. And then a binary plus. Operator is going to be same. The left-hand side is going to be the same as the name, so that's going to be name. The right-hand side is going to be 1 casted, which is up here. So basically it takes name plus 1. So this binary operator is name plus 1, or I plus 1. And then we're going to assign name equal this post statement, which is I plus 1. Declaration name token. So I think this is handling everything. Fuck, this is annoying. Okay, that's better. So now we can just fill in this is an assign. That's a post statement. Expression statements. All right, that's it. That is parsing the loop, and I'm just going to return this loop body. No, this entire loop. So that's a loop. Yeah, this could have been done really simple, actually. I just need to figure out the naming. This is actually a place where like function overloading could be really nice. Yeah. Because kind of the work is the same, but it looks so much here. And by avoiding this operator, that might help. Actually, do I need to have this operator? I'm gonna try to avoid this, because this is only gonna happen if I have an error. And I won't have an error because I'm making this. Yeah, I think so. Yeah, something like this. It's gonna return the loop. If statements, I'm gonna just do the for loop first. And data, what was that, like 20 something? So I'm gonna loop from 0 to data. I'm gonna print counter and a decimal number, which is I. Okay. Let's see if I can parse this first. I think I handle everything. And no name parser. I'm missing a capital letter. Oh, there we go. That was why. This is supposed to be copy token. Copy token. And I have to make sure that I'm doing this expression cast on all these assignments. One. This is the statement. Statement. Where exactly is the problem? It's just a name. Okay, so that needs to be an expression. Okay, fine. This is actually cool. To a expression assign. Where is the assign? There we go. This is horrible. Oh my god, that's horrible. And we have a statement kind not handled. The good news is that this is like, we're done now. The printing is really simple because we have functions for it already. This is type. This is a statement. So we want to make a function for printing a loop statement. So I'm gonna first do indented print and loop. I'm gonna indent here anyway. Indentation plus plus. Indentation minus minus. And here I want to like print the condition, the body, and the other things. In Rest, one would do step by two. Okay. Yeah, I like the Rest way like a Rest method way better. Like way better. The Python way is really unclear. Yeah. So indented print. This is an init. And we're gonna assume we have, this might not be right for all the loops. We're gonna just make it work for this one. Indentation plus plus, indentation minus minus. So this is the init, and then we're gonna print, this is an init statement, I think. We don't really need to use any statements for that. Actually, it's wrong to use statements for that. Okay. Well, it isn't really wrong. I'm gonna just go with that one. But it isn't necessary. So init statements. So that's the init. And then we're gonna have the condition. And then we're gonna have the pos statements. And we're gonna have the body. So this is just a body. That's fine. That's a statement. I think this is like condition expression, so we're gonna have to print an expression instead. Additionally, I want to track the indentation here. So I'm gonna say loop indentation is equal to indentation. And then after the loop, I'm gonna paint the loop indentation, like the line which goes below the loop. And then before the last one, which is the body, we're gonna clear it. Oops. So now we have a loop. We have an init, which is just I is equal to 0. Condition, which is I is less than data. The pos statement is an expression. Don't really know why. I is equal to binary plus I plus 1. And the body is just a compound statement. So that seems to work. I'm still looking up the function printf. Oh, yeah, it's supposed to look it up. It's supposed to ignore the errors. And we have a typer statement is not handled in the typer. So this doesn't really do anything except that we have to go through all these things and just type everything. There's going to be a little step in the typer as well. Thank you for following Super Winner. type statements. We're not gonna, this is just a normal statement. We're just gonna like iterate through all these things. So that'll be type statement on loop init post and body. And then we're going to type the expression from loop condition. Typer. So now we should go in there. And now we're going to have a... Oh, we're missing a T. So it's trying to... We have a segmentation fault. For some reason. This is weird. I guess it has to do with the typing stage. Thank you for following. When I'm making like a 0, it is supposed to have a type. I'm gonna actually install the debugger the next time, so I can debug instead of just printing. But I guess it's in here because it didn't happen before. So it's entering and it doesn't exit. Let's see if it's exiting that one. So it's in the first statement. Loop. This is the init statement. So I'll have an expression statement after. Yeah, so expression is after that. So I have a segfault in the type expression. So remember, the first one is supposed to be an equal, like in a sign. So I'm typing a binary expression. I'm asserting that binary has a left and right, and I'm typing both. I guess the declaration are wrong. Because this is firstly typing the binary left, that is ending up in the primary. And I'm here looking at this. Thank you for following. So I think the primary is wrong. I think the primary is wrong. We're setting primary identifier. Like, we're not pushing I on the scope. That might be the problem. So what I'm gonna do, I'm gonna push the declaration on the scope. I'm gonna push this declaration on the loop body. Whoops. Compound scope. Where is it failing? So let's see if it can type the right hand side. It doesn't type the left hand side, I think. Yeah, it doesn't type the left-hand side of that sign, which is supposed to be 0. So this is typing an expression with the left-hand side. And this is the init. So the binary equal. So this is a number which is 0. So how does it parse a number? If this is a number, it just gives it the type, which is U64. I don't have any experience with block change. I don't know what that is. How did you make VS Code look like it? I don't know. It is looking like a mess. It's really, really bad. There's way too much colors. Can't really focus with all these colors. But I have like a... I think it's on my GitHub. This is a little bit of a different color theme, which I sometimes use, but it's in here. All right. Yeah, it goes there. In something. We know where the error is happening though. It's happening in the left. So let's just make a line separator and try to track down exactly what's happening here. I think it's in the number. It should be a number. No, it shouldn't be a number, it should be an expression. I don't know, we're out to see. So we're entering. I don't know why it's saying we're doing the right hand side first. The right is right. The right is right. The left is wrong. The left hand side is the I, which is an identifier. So before this, like after this line, we should have an identifier. I'm doing something weird. Okay, so we're getting the number there. It's assigning here. It is assigning. It's looking up in the current scope. What is the scope? Primary name. Maybe this is yielding a segfault. I think that might be the case. I'm gonna move this up. I'm gonna just assert primary name. I'm gonna say the address to primary name. He's gonna try to do that access though. Dang it. Typer. Why the hell doesn't it have a current scope? It does have a current scope. Here it's gonna error. failing there. It's failing in a lookup. So this is where it fails. Okay, I'm gonna delete the printing. We don't need the printing anymore. And I'm gonna print what we're actually looking for. So we're looking for I, and we're looking up in the current scope, which means we're looking up in scope. They should also be fine. I'm a little interested in what the current scope is. Like what is the address there? So this will be typer, and that's a pointer. This will give me the current scope, which seems right. First of all, let's print the scope in here. My segmentation fault before it returns. It returns. Okay, what is it returning? It's returning 0. Oh, fuck. That's so stupid. It's because the I doesn't exist on the current scope. I have to manually enter the scope in a typer. The reason it doesn't work is because I removed the type thing, which was beyond stupid. Looking up a function, I think I can delete that as well. Enter, exit. So all this is gonna like live in a scope. Yeah, I was telling like I'm not gonna do this mistake, but apparently I'm gonna do that. I think we have to enter scope. I'm gonna give it a typer. The scope is gonna be the loop body compound scope. This is what we're gonna enter. And exit the scope typer. Oops. So I think I've removed all the printing. So now it should first of all work. Typer current scope failed. It's returning 0. Enter scope. It's gonna delete that. Thank you for following. Thank you very much. Before, what am I talking before? Before that's an identifier. I don't know why I'm using that identifier that much. The current scope failed. I'm getting the before like I 4 times. I'm making my own language, yeah. This is such a simple thing, and I think everything is just because I'm making these structures myself. They're so error prone. Like, where is this happening? Typer 37. Is that 37? I'm exiting a scope. Oh, dang it. Okay, I'm gonna move this up here. I'm gonna type in just in a statement there. Actually, I'm gonna move it down there. This has to be outside this exit scope, because this is actually exiting that scope. It's very stupid. Yeah, generator is starting. So it's typing something. Yeah, it's typing this. The inference is working, at least. So I think we can just start generating this. So we're gonna generate a loop. And this is actually simple, because all the typing is being done already. So this is a loop. We're gonna do some initialization first, which is assigning 0 to I, and then we need to have the condition. And if the condition are not satisfied, we're gonna jump to the end of the loop. So you're gonna have some like start, we're gonna have some end, we're gonna have some init, and we're gonna have the condition, jump end, question mark, and then we're gonna have jump start. Does this make sense? You first initialize, and then you have some kind of start condition. This is a start label. So basically you can jump here. And then you're checking the condition. If this is not satisfied, you're gonna jump to the end. And this is just continued execution. If the condition is satisfied, it is not jumping, so it will continue to execute the entire body here down to the jump start, and it will jump again up here. So that's how we're gonna implement it. So you're first gonna generate a statement. Statement loop. In the statement, that's the first thing, and then we're gonna emit the start label. There's a label. I'm gonna place it here. So this is gonna be a loop, and we're gonna give the number. So I wanna have this counter here as well. So loop counter equals 0. This is gonna be a static variable. So this won't change when we exit the function. This will be like as a global variable. And we give it a label, which is the loop counter. And then we do loop counter plus plus. And then we generate the expression. So that will be the loop condition. And then we're going to compare 1, 2, 3, 4 CMP. Can you do like 0 with RAX? Or do you have to place this in a register first? I think you have to do that in ARM. Maybe I'm wrong. I'm gonna generate. We're gonna generate the jump first. Jump if equal EQ. You're gonna jump if this is if this condition is false, you're gonna jump out of the loop. So if this is comparing and evaluating to 0, so if they are equal, jump if equal, and then we're gonna use the same label. We're gonna make a label for the end. Loop, let's call this loop start, and loop end. This is also a label. Loop counter. So jump if equal to loop end, and we give it a number, which is the loop counter. So this is tracking the condition. And after the condition, we're gonna just do the body, I think. Loop body. And thank you for the follow, by the way. And then the pause statement, which is gonna happen after the body. So generate loop pause statements. And then this is gonna emit, this is gonna jump again. Jump back to the loop start. Okay. So this will jump back here, which will evaluate the condition once more. And emitting a loop, okay. For JE. Is that instruction is a JE? And there we go. There we go. That's a loop. Counter. We're printing the counter and I. And this is going from 0 to data. Let's print what data is first. We don't know what data is. So we said that the data is 26 and it's going to loop from 0 to 26. That's working perfectly. That's so cool. That is really awesome. Loop within a little break, I think. Yeah, because we're having the loop counter plus plus there. So we have to say that counter. So I'm gonna say like number is equal to loop counter plus plus, and then we use the number here instead. And then it should not break. Loop counter. Where's the problem? Oh, static number. That's not supposed to be static. Okay, so for each of these, I'm gonna do for j in 0 to 2. So I'm gonna do it 3 times. And we're gonna map this one to the j value. So 1, 2, 3, 1, 2, no, 1, 0, 1, 2, 0, 1, 2. Okay, so it's working. But I guess that you're right. I had to fix the counter. Thank you very much. That was a good observation. Very nice. Yeah. So the first thing I'm gonna really fix like later is this like parser function, because that's horrible. Oh my god. This looks really bad. The rest is really clean though. It is just that when I'm constructing some tree operations, it's very annoying. So I don't know if this is getting easier like in the typer or probably in the generator. I sort of want to have the tree parsed first. So I guess this is the way to do it. I just have to clean it up. How much is the clock? 21:45. We have been streaming for 6 hours. Okay. We can try to make pointer work. So I want to have a function. Let's just call it like f. This is a function which is taking in some kind of data, which is a pointer to a U64. And it's not going to return anything. And it's going to say, I want the new variable to be equal to data, the value that data is pointing to. And then I'm going to set variable equal to 56. And then I'm going to store it back into data. I just want to check if type inference are working like correctly there. So this is what I want to do. And then I'm going to say variable, I'm going to say like x is equal to 1. And x is some value. And then we're going to call the function which is going to modify that memory address. So I'm going to call f with the address of x. The address of x. This is really into like, I don't know if I like having pointers be this, to be honest. That makes it really confusing for me. It's like having to change 2 things instead of having to change 1 thing. So I don't know. Are you sure you want pointers in your language? Yeah, I want pointers in my language. You can do very much cool stuff with them. Yeah. Yeah, them. I'm just thinking if we're gonna switch those 2 operators. Well, this is gonna work. So we have like an address of a U64 and we're giving it the address of x. So this is gonna change x. And it's still like compiling. Oh, it's running the previous program. I'm doing expecting 0 but got a comment. Why is it expecting 0? That's stupid. That's a stupid error. What the hell is it expecting 0? Oh, dang it. I have this error handling in the Lexer So this has to be the same as the Lexer enum table, what do you call it? That has to be equal to this. So we have to update that one. That was stupid. So we have number string identifier comments. So number string identifier comments plus minus multiplication division equal, less equal, greater equal, assign, and we have not equal. This is right. And then we have dot and double dot here, semicolon and comma, and we have and as well. Okay, so now it should work. So this is the function f, and this is the body. So we're taking in a pointer to unsigned 8 bytes. We can see the type inference is working. So the variable is now actually getting the type unsigned 8 bytes, because that's what the data is pointing to. And then I'm having a deref. This is stupid. I don't know why that's happening. That is maybe like, that is happening if you have a pointer to something. If I'm annotating some node with a pointer to, it is not going to paint this one. So probably I need to, when I'm typing all these expressions, I need to check if that's supposed to expect something here, and if it expects something there, I'm going to paint this indentation there. But that's not important. And I'm doing equal, setting this equal to 56, that's fine. And this won't work, I think. Here we're dereferencing data. So I don't think we support it. Generator 86. We're having an error in the generator. Number 86, which is a number I can search for. What the hell? Is that maybe the big error I was issuing, like the big number? I had a big like exit with a big number. This isn't really expressions not handled. Oh, expression unary. That was a big number. I don't know why that's the case, but I think you can't have an exit status code on Linux which is above 8 bits. Above 8 bits. Okay, so let's handle a unary expression here. So this is like a pointer. This is not a pointer. I'm just going to call a function which handles this. Handle generate unary expression. Okay, so this is the unary expression. We're gonna have to generate assembly code for it. So I think if I'm not mistaken, we have 2 different cases. We have a unary deref, which is what I'm trying to do here, and we have address of. Doesn't that work? So deref and unary address of. We have to implement both. So here we're taking the address of. We're giving this function the address of x. And the deref above. And if nothing here is working, we're gonna yield an error. This is in the generator. Generator exits. Okay. So, what should we really generate here? We should generate the address of x. And when I'm actually generating an expression, this is basically I'm generating the address of that one. And I'm generating the address of x. So here I should call generate address of whatever this is pointing to, if that makes sense. So unary operand. I'm going to generate the address of the unary operand. And that address is going to be stored in RAX. So this will store the address of x into RAX. And if this x, like, well, okay, let's see. So in this case, the unary operand is just the identifier x. And we have the generate address somewhere. This is just checking that it's a primary expression. And if it's an identifier, it's going to load the address of that identifier, which is some kind of offset from the frame pointer or the base pointer. So the only thing we do is to generate the address of this. That's it. We're not going to do anything more. In case of a deref, see if I have like something like this. I'm gonna thank you for following. This basically means place 56 on this address here. Okay, so I'm calling this in an assign. I'm assigning this. Or I'm assigning stuff. Where is assign? So I'm generating the address of the left-hand side. So this will be like in the generate address. So this other thing will be like this will be handled here, while this is something like this. So in this case, I will just load the address. So this basically means we have to interpret the data as an address. And we're going to load whatever is at that address, we're going to load into the register. So I'm actually going to assume that whatever is in here is an address. And the typer should actually check that. So this is supposed to be an address. So we're not going to generate an address, we're going to generate the actual expression here. So here we need to generate the actual expression. Operand. So this is generating whatever is here into the RAX. And then we're going to load from the address of that. So I'm going to load from RAX into RAX. And that's loading that. And then we have to fix what I'm assigning. So this is going to generate, where is that? this is gonna generate the address of the left one. So we have to figure out what is the address of this. Well, the address of this is just equal to this expression here. Like it basically asks where I'm gonna store the data. This asked whatever, where it's gonna store the data. So in here, I have to handle what happens if I have something like this. So if it's something like unary, I'm just gonna generate the expression for this. Isn't that correct? Let's, oops. Primary kind. We have an expression here. Okay, so I'm not gonna write it there. We're gonna have an else if. If expression kind equals expression unary, and this is like a deref. And if unary kind equals unary deref, we're gonna compute the expression here. Generate expression from this unary operand. Yeah, and what if we have something like this? That won't work. Because you can't say that, so that's going to be handled by the typer. This is right. I'm just going to check if this... I'm taking in a pointer. I'm resetting whatever this is pointing to 56. Yeah, okay, so if I'm switching that, it's gonna be like this. I don't like that either. So I'm probably gonna just use this. Let's also say like if it's not none of those. This is in generator. I'm gonna say address. Oops, I'm a little bit slow when typing. It's gonna go up. I have to just be like accurate. I have to focus on the accuracy instead of just the speed. I think that's important. But I'm learning like how to type in Dvorak. That's the reason it's very slow. And this is like primary kind not handled. And this will be unary kind. I don't know if this is necessary. Let's see. What the fuck? That's working. That is working. You can see we have an x is 1 because we're setting it to 1. And then we're, yeah, changing it to 56. So that is working. When I'm allocating the stack frame, I think I can support like arrays. Doesn't this mean that arrays also should work? If I have like an array? I don't know. Taking the pointer. I'm just trying to, I'm gonna try to make, I'm gonna check if arrays also work. When properly used, yeah. What does a double dot do? That's a range. So this will iterate I. This will make I go from 0 to data as an iterator. From 0 to and including data. That's a double dot. So powerful. Range. You can learn on 10 fast fingers. Yeah, I'm using something else called like typing practice. I'm googling. I'm googling after typing practice, and it's the first hit there. Like I can. I'm usually doing this one. Gonna just sign in. There's an internal server error. Stupid thing. I can at least show you what I'm using. I'm using this one. But it's so hard. Anyway, I don't care. It's hard, but it's a lot easier when you can actually see the words. What code are you generating for printf? I'm not generating any code for it, but that's a good question. Because this is really system calls. So they will go, there's like an instruction for a system call, and you place stuff in special registers, and then the operating system will handle it. Thank you for the follow. And I'm not implementing that because I want that to be typed in the language itself. So I want to have like assembly functions in a language. So for example, system calls will be written in assembly functions because I think that can be quite clean. So until I have assembly functions, I'm just going to do this. I'm linking it in with this stdio. Let's see. Where am I linking it? Am I not linking it? I thought I was. Why the hell is it working then? Is this automatically gonna include some libraries for us? It doesn't seem I'm including that. But I'm basically using like the printf from GCC or whatever. I think that's the linker is gonna figure it out for me. I don't know. Yeah. Let's take and check arrays. So I want to have like array. This is gonna be 3, 3. Yeah, 3, 3. Let's make it U64. I want to allow smaller numbers, but then I think I need to change the access functions in the generator because I can't use like move to move like an 8-bit number. I have to move. What is the instruction for move like a byte or something? There is an instruction for it. Like move. Yeah, byte. Yeah, something like this. We're gonna check it out. let's have a double loop. And as far as I know, this will just be local to this scope here. So I can reuse these numbers. So I'm gonna say data that is equal to 3. This is the size. And then I should be able to say size minus 1 and 0 size minus 1. And then I'm just gonna set these values. So I'm setting it to, like, I'm having a counter, which is 0, and I'm setting it to counter, and then the counter is equal to counter plus 1. We don't have plus equal and we don't have plus plus yet, so that's why I have to write it like this, but that's fine. Yeah, so this will be I and J. And this is an array. Wait, is it? That's being casted, like, it's ending up with some kind of deref. It's ending up as a deref. So I'm gonna have data. This is a pointer. I don't have cast yet either. So I'm just gonna use the value. So this is a pointer to a U64, and I'm gonna assign the value of array, which is a deref, which then should work. So array is the same way I see this is just a pointer. And then I'm gonna say for I in what's the 9, which is the total array, I'm gonna just print the value of pointer. So print data was pointer is equal to pointer plus 1. So this is also going to check that I'm not adding 1 here. I'm actually adding 8, because 8 is the size of U64. So this is supposed to add 8, even though I'm writing it like this. So let's hope it works. Nope. Didn't work. Oh, I'm using the fucking wrong syntax again. It's dumb. Variables are not declared. I was having a typo. It is very nice with like a checker like this, so we know where you have written something wrong. There is still something wrong. Let's print the pointer instead. Just the pointer. So I'm replacing this with a pointer. Okay, so the error is happening up here. Okay. So the array is I'm deleting this. I want to print when I'm assigning things at the stack frame again. Compute locals. I want to print this. And what offsets? I'm gonna print this size first. I'm gonna just print the size, which is declaration type size. Alright, so this is what I'm setting aside on the stack frame, and the size is wrong, as you probably see. So for example, the array is wrong, because this is a U6, like, this is supposed to be 9 U64s. This is an array, and this has size 8. So that is probably right if it's interpreted as a pointer. But this is supposed to be like 9 pointers, 9 objects. Yeah, counter misspell, thank you. Nice, you're nice that you're following. I'm keep forgetting those things, especially this one. This is hard to know. So I guess why it doesn't work is because we have the wrong thing, and if we're calling something, and that's gonna mess up the call stack entirely. So what is really wrong? We have a type that has a wrong size. That's the issue. So this happens in the parser when parsing a type. This is parsing a type. And we're always setting the pointer here. This is the issue. No, this is the array. Okay. So by using this is pointer, it will automatically get the size 8. Like that pointer size will get the size 8. But this is an array. So I might want to increase that size. I have to cast the type to get that size. So I'm actually going to do like type instead here. Type pointer, count is equal to token number. And then we can also do like type size, we can change the size as well. Question is the size going to change there? Like here I'm having an array type. And it really makes sense to have the total size there. So I think I'm gonna saying if no, this is gonna parse a number anyway. Doesn't, yeah. So I'm gonna say type size times equal token number. Oops. And then we just return the type. Okay, so now we're getting something better. Array with size 24. The problem is that I'm not gonna, this is not really, like, I don't care about the size. I have to set the size equal to the number of elements, times the previous size. So I'm getting the previous size because this is pointing to something. Okay, so I'm gonna fix the size down here. So we first determine what it's pointing to, and then we set the size. So this will be number of elements. I'm not gonna call it count, I'm gonna call it like, yeah, I'm gonna call it count. This will be like type pointer count times type pointer to size. So you take what it's pointing to and you multiply by the number of elements it's pointing to. And then you're going to get the right size here, which is 72. And all right, we're just looping here, that's fine. And then we say data was, and we print the pointer, which is an address of a U64, which is an array. How is the tree? How is this looking? Loop before the loop, probably. Okay, so reassign. We assign a pointer to unsigned 8 bytes. So this is actually requiring a cast. To an array of 3, unsigned 8 bytes. So this is really array. What is assembly code like? Let me make a label very quickly when we do this. So this is the assign stage. Assigning. Thank you for following. Thank you very much. So a binary, we always start with the right-hand side. I'm not sure what we're printing here. Yeah, I guess since this is the left-hand side, we're starting with the array. So this is the array. And we're loading the address of that into RAX. And we shouldn't do this. This is wrong. Yeah. Thank you for following Puppy Codes. And we're pushing racks. And then we're loading this new value, which has a lower index, which is right in there. And then you pop it, and then you store it here. So we store at the address. Which is this? No, wait a second. Yeah, okay, you're popping into, so this is right, but we're dereffing here. So basically what we're storing, the thing that we see here, you can see it's incrementing correctly though. It's incrementing correctly with 8 bytes at a time. But we're storing 0. We're basically storing what that's pointing to. We're storing the first element in this array, not the array itself. And that's the right-hand side of the expression. So let's okay, so here's the sign. This one is wrong. This is like we're pushing the racks. Generate expression. That is going to be a unary, which is going in here. So if I have a deref, which is the case here, I'm not going to load it. I'm not going to load it here. Because I am loading it. Hello B4141, welcome. What is weird in... Yeah, that's a like custom theme. Yes, it's this language here. I need to make some syntax highlighting for this. It shouldn't be that difficult. I think VS Code has support for it. I'm questioning if this is right, if this is correct. Because here it's basically saying some... Wait a second, no. It's just an array. This is just trying to load an array. So the address here is gonna be wrong. In the generate address, we have to check if this is an array. I think we have to check it here. So this will be a primary identifier. And if that type is an array, we're just gonna load the address. We're not gonna... It's generating address. Okay, where's the primary expression here? Here's the primary. So if it's a primary identifier, it is generating the address and loading from array_x. That is wrong. That is the case if this is not a pointer, or if that is not an array. If this is an array, we need to just generate the address. So this is the case if it's not an array. And we know everything, so we know the declaration, so we know the type. It is specifically if that is an array. So I'm gonna if type kind equals type pointer, and primary declaration type pointer counts. That is an array, so else. I'm just gonna check if this is working. So now we're getting an actual address here. So if I now assign this, is equal to counter let's try to return at this point. Okay, so now this is the issue. It's generating this. Oh, I'm scared. Thank you very much. Is it doing the right thing though? I can check that first. So the body is doing a binary assign between this counter, and we can see it has the same sizes though, which is correct. So it takes I plus 72. Why the hell 72? The 72 is wrong. Is 72 maybe 8 times 9? Yeah, that's 8 times 9. It's in the plus. I know where the issue is. It's in the typer. When we do this crap here. Type binary. We're basically constructing a new node. Thank you for the follow. Hamatu Hoshi. I hope I pronounced it right. Probably not. I think we're... It seems we're using the right pointer as well. This is a binary left, type pointer 2. This is what it's pointing to. Assert size. Size is 72. Something is generating size 72. Which doesn't really make any sense. So it's multiplying I. So this is the thing which is wrong. The left-hand side is an array of 3, unsigned 8 bytes. So this should be 3 times 8. Not 3 times 9, not 9 times 8. So maybe we're accessing this before we are supposed to. Because I know it is binary. Left. Pointer 2 size. Pointer 2. This is accessing what it's pointing to. Let's if I'm printing this, I also want to print what the actual data member is. Just the type size. So the type size is also 72. So both what it's pointing to and the size itself is 72. Which makes me believe it's in here when I actually set a size. It's all okay. Okay, it wasn't that far. I feel like a small brain. No, this is not... yeah, I'm just... I don't know. I think that might be because I'm setting it up so confusingly. There is one place I'm assigning the wrong size, and that's making it access memory is not allowed to. That's generating the segmentation fault. This is square bracket. I'm parsing a type. This is generating a new type. Pointer. This is the number of elements times the pointer 2 size. I'm gonna print that. Parser size. Thank you for following. Thank you very much. So the pointer size is this. count. It is before here. So the count is 8. Says it's 24. Okay. So size, that's 8. This is correct. It's getting U64 is 8 bytes. And it's having 3 elements, which gives us 24 on the next one. And 3 elements there as well. So the last type will have size 72, which is correct. And that's the type size. So the type I'm actually returning there. So this array has type size 72. So when I'm returning, I want to print what this is pointing to. Size of pointing to. This will be type pointer pointing to size. That should not be 72. Yeah, that's 24. All right, so this is correct. Thank you for following. So we can assume that the error is in typer. But I'm accessing pointer to. Crap. Pointer to size. This is wrong. So maybe something is like being a pointer to array. Wait a second, I think I know where the problem is. When we have an array, we're basically making it a deref instead. And I think we're making it a deref on the fly in the parser. So that might be the problem. If this is an open square, we're having a deref. Okay, so this is the problem. We convert this to deref. Does the deref have a type? Is the question. We convert this to an offsetted deref. So this is converted into some deref expression if I have that. Which means I have to find the type of the primary expression. Okay, I think we're getting closer. The point is that when I'm making a all right, so this has to type something like a double array of 64, whatever. And this is eventually going to be like, or this is not the problem, this is the problem. So this becomes array plus I plus j. And I'm converting this to this in the parser. And at that stage, I do not know what array is, what type that has, because that might be declared later. Like, this is gonna work. We can just have it like that. That's gonna work. So this is just the structure, and then I'm going over this after in the typer stage. And then I apparently am assigning the wrong type here. So this has the wrong type. So when I'm adding I, I'm basically adding too much. It's an array. Now there's one place in the code where I'm missing, like, it should be pointer, the type should be what it's pointing to, but not the pointer itself. I know exactly what is going wrong. I just can't remember where that is. Just gonna say the same thing, yeah. I think that's a mistake. If that was what you meant. Crap. 10 points to the person who know where the mistake is. Unary primary. That's right. It's actually right. But now I actually know what's going on. It is two places it can go wrong. It is when we make this, then we're not typing anything, because this can be declared later. And we know the type of this. Or am I just stupid now? Is this really allowed in C? Like if you have an array like this. This is where it goes wrong. Primary number is equal to size. Size times count. Size is then way too big. Size is 72 in the beginning. So we're accessing the type of this one. So we're looking up the type here, and that is correct. So maybe since this is an array, we're going to use what that's pointing to. This is what is declared as. Array is an array of 3 8 bytes. We're reconverting that. Maybe I have to check if that's an array and just assign a different type. This is just an identifier, okay. So I'm assigning an identifier here. This is the identifier. And I'm looking up in the scope. So here I'm assigning the type, which is wrong. The type is, I knew that was wrong, but it says that the type of the array is that. Wait a second, type of the array is that. It is right. It has to see what this is pointing to. And this is pointing to an array of this. Fuck. That's not something. This can't be right. This cannot be right. Type pointer to size. I'm printing both the size of the type and the pointer to type. Let's see if there's something interesting happening. Oh. Size is 72. So first run, it's 72, 72, 24. So this is 24. Why is size then bigger? 24. Oh, fuck, crap. This is not supposed to... we're not gonna care about that. That's being handled in the parser. The size is increased in the parser. Wouldn't it do, like, multiply by like a number of things there? That's the thing which is wrong. So we have the size, and that is the correct size. Always. So this is correct. We still have a segfault, but I think that's... So now we're increasing I by 24, which is correct. And this array has... The array has this type. And when you add them together, it is still going to have this type. You deref it is going to have this type. Then you add to something else, it's going to still have this type. And you deref that again, that's going to have that type. So unsigned 8 bytes. Let's move this up here. IJ. Where's the segfaults? Can I print something in there? Iteration. It's doing one iteration and then it's failing. Is it practical time-wise for one person to build a complete language and a compiler? I think it's worth my time. If not, this is going to be like, this is probably not going to be a good language, but it's going to be good enough. And I'm going to learn like a huge amount of programming from doing this project. So that's really the main reason I'm doing this. The question is, have I changed something trying to get this to work? Which was not supposed to be changed. So this is the pointer access. So I'm loading. That's assigning. I'm always computing the. Do I have any immediate values? I'm having 8 here and 24. Okay. So when I'm loading here, I'm basically accessing the value there. I don't think this is right for arrays, because I think I'm accessing the array there. Let me actually check that, because I'm assigning an array with size 27. I'm gonna print the offset as well. I want to know where exactly I'm assigning that. I'm gonna choose this offset here. So the array goes at offset 1112. 128 is counter. Okay, so this is an equal, so it's computing the counter first. And this is correct. It pushes this. It loads 8 into racks, pushes racks, loads 8 from RBP. This is A. No, this is J. Okay, so J is the index at RBP. And it finds the value of J, pops it, and multiplies them together and pushes it. Yeah, that's correct. And then it moves. It's doing this first. And then she'll add that with array. So this multiplication is happening here. And then we push the result of that. And then we're not supposed to move this. We're supposed to add it to array. This is happening first, and then we're dereffing it. We're dereffing an array. So something's not generating code for the name. So where is my primary generator? Here we go. If this is a primary identifier, which is the case, then we emit something. I'm gonna emit like that's a primary identifier, okay. Yes, that's correct. I don't understand why that's happening there. It is taking the 8 first. Okay, it's taking the 8 first. Taking this first. Because this is the right hand side. So that's correct. And then it goes down here again. Finds I and 24. So pushes that. So 16, that should be I. Offset 16, that should be I. Where's it? There we go. And it's finding the address, the content there, and it's popping the original into RDI, and it multiplies them. So whatever's on the stack at this point is this part here, and then we actually load the array. So this is where things might get wrong. We're just loading the address. We're not accessing anything there. So just loading the address, we're adding that. This is correct. To RAX. This is wrong. Shouldn't there be like a pop RAX before this? Because we're assigning 128. That's a counter. And we're loading the value here, which is in RAX. We're pushing the RAX. Yeah, we're pushing the RAX. Move the value at RAX into RAX. Oh, this is so complicated. This is doing the last addition here. That's doing this part, the binary plus. And then we're dereferencing that again. So we can't really deref A. You can't really do this. This is wrong. This is not generating a valid address. This is some element into the array. If that's going to go in here and you try to do this, that's not right. Still in RAX. Yeah, this is wrong. You have like a to-do list. I can make it to next time. I don't know what the clock is. Like 11. Yeah, I can make a to-do list what I plan to implement. I can do that. Hello Sebes, welcome to the stream. We're working on pointers, trying to get pointers, like more specifically arrays. Trying to understand how they really operate. But it's difficult. I think okay, let's go back to the code again. I can probably comment this instead. So this is array plus I plus j is equal to counter. So I'm first making that one, that's fine. And this is an assignment. So this is failing, and that's an assignment. So we have to start here, and this is returning. This is correct. And then I'm having to generate address of the left. I'm trying to generate the address of this one. And since this is a deref, I'm using the pointer. This is deref. Yeah. So since this is a deref, this will generate the address of this part, because we're dereferencing that. This basically tells load to whatever this address is. So this will give us a new binary expression, some kind of binary expression. Here, binary plus. So for general binary expression, we're first doing the right, and then we're doing the left. And we keep them in two registers. So I'm generating the left-hand side, which is this expression. So I'm generating an expression that's in a deref. Where's the expression again? There we go. This is a deref. This going up here. And we're generating this. And that's generating the expression here. And it is loading from it. I'm totally lost here. Yeah. What happens instead of I forgot to subscribe or follow? You can follow. That would be appreciated. What is happening? So we're trying to generate this expression here, which is very simple. And this is converted by the parser to this expression. So you take array plus I. I can show you here. So array is an array of arrays, so it's basically pointing to an array of 3 U64s. So array is pointing to this thing. So we're incrementing that by this thing here. Since this is an array, it shouldn't really deref here. Since this is an array. There is something with the array thing that I don't understand. Because array and pointers are very similar in C. They're handled a little bit differently. More specifically, when I'm computing the address, that's handled differently. So I think that when I'm actually doing the pointer, that shouldn't really deref, because this is an array. Because what this is, okay, so this is a pointer to an array. So if I'm taking this plus something else, this is still a pointer to an array. So if I'm doing this star, I'm actually trying to load an entire array into memory, which doesn't really work. Good to see you again. Been seeing a lot of JavaScript, Python, React. Yeah, that's cool. Are those pointers loose? Yeah, they're kind of loose now. So the problem is we're trying to load an entire memory into an entire array into memory. That's the problem. So I'm actually going to generate the expression there. This leaves me like a little bit unsure. If I'm gonna generate an address, because this is really forcing us away from this generate address thing. Here I think things are working. So if I'm gonna generate an address of this thing, and this is a unary, I should generate the address of the resulting thing. Or whenever I have like a deref, I shouldn't really again. I'm gonna try to generate the address instead. Expression not handled. Yeah, okay, because it doesn't really do that. We're trying to load an array into memory. How do we prevent that? How is that really? If the primary is an expression, I think it has to do with the unit. Like, there is really very few places things can go wrong, and apparently all those places it's going wrong. If this is a deref, we're gonna generate expression or address. Okay. So when loading in the address of this, I will ask the address of that one. If that is an array, I just have to load this into memory. And if I'm asking about this, this is also an array. So I can't load that. Where am I loading this into memory? If this is deref, I'm loading it here. I can't load it if it's an array. if unary operand type, the pointer type pointer is valid. If it is, I'm gonna check that here instead. I think this is the correct place for checking that. Maybe this is gonna be there instead. Primary. Yeah, so primary, we're just gonna load it from the RAX. We can't really do anything else. So I think this is gonna be like this. And here we replace the primary with a unary operand type. I don't think we need the declaration there. Operand if this is a pointer and the count is something, we have an array access at the very end. One array access. And if I'm actually mating this, right before I'm actually accessing this memory, it is happening here. So I'm not loading this into memory. Does a 1D array work properly? That's a good question. We can try with a 1D array first. Should be the same though. Array of 1. We have arrayify, so array of 1 is working. Okay, so I'm gonna do 9 here instead. We have an array of 9, and then we set array of 3 equals 45. And then I'm just assigning I'm saying that this is a pointer to U64, and it has this address of the array. And I'm printing that. This is the array. This is supposed to be in the primary as well. Primary number identifier. Yeah, we're gonna load from this one. No. It's gonna be like this. Oh, it's primary declaration. All right. So now I'm printing the pointer instead. So I can print what the pointer is pointing at by doing this. And I'll get, oh, I'm printing P here. This is supposed to be D. I'm getting 45 on 0, 1, 2, 3. So 1D array is working. The question is, why doesn't 2D arrays work. Which is a little bit strange. The mistake can either be here, it can be here in a deref, or it can be in the address. One of those places. If we're generating an address for okay, wait a second. Wait a second here. Excuse me. If I'm generating, let's go back to the previous example. If I'm saying this is not gonna work, like 2, 2. Then this is transformed into array plus 2 plus 2. The problem is that here I'm trying to get the address of that one. I'm trying to compute the address of a unary, which doesn't really work. If I'm trying to generate the expression from this, it is going to try to load me stuff. I don't want that. So here, I'm actually forced to check if this is an array. If unary operand type, if that is a type pointer and a unary operand type a pointer counts. So this is an array. If that is an array, we're just going to generate the address. Expression not handled. I'm generating the address of something. I'm probably really stupid now. The problem is we're trying to load something into memory we're not allowed to. This is supposed to be expression because it might be anything. If I have a deref, generate expression. Okay, so I'm having this and I'm generating this expression here. And this is happening apparently. I'm gonna try to go through the assembly code again. Here we go. What the fuck? What the hell? I'm actually like element 2, 2, which is the last element. saying 9. So this is going to be from 0 to 8. So the last element is 45. How do I... If I set like 1, that's equal to 4. Do I have 4? No. So this means that the second element is going to be 4. And it is. Fuck, what's... Why is this working? So what did we do? We checked if this is a pointer. It is not going to try to load an entire array into memory. Do not try to into memory. That makes sense for me. That makes sense. Additionally, if we have an identifier like this, and this is a pointer, this is a pointer, it is not going to try to load it. It's just going to generate the address of that one. And then the address function only generates the expression again. Makes sense. Let's try to make something more complicated. Let's take a function like print board. This takes in a pointer to a double array of U64. So this is the board. It takes in a pointer to that, and it's gonna try to just print it in a nice way. This is like tic-tac-toe. So we're gonna have a for loop. So for I in 0 to 2, and for j in 0 to 2. Actually, we're gonna print the lines here. 1, 2. If I have the number underneath, it's gonna be like 3 lines here. If I do this inside here as well. I'm just gonna print an X here. So we print space, X, space, not new line. And then we print a new line here and the ending there. It's going to print a board. It's going to take in the address of this array. So I have to give it the address of array. Print board. Oh. We have an error. I'm not supposed to do that. This is an address. All right, so it's printing as expected these X's. So I'm printing the game here. So now I need to check if I need to print an X. So I need to have if statements working. And that is just really a condition. I think if statements are really fast because we're not gonna have to do this stupid thing with making these things ourselves. So I'm gonna try to make if statements. Can we parse this? Parse if statement, okay. So the parser is currently pointing to the first word, so like the if word. thank you for following. And then we're gonna get the token is equal to next token. So you're gonna get the one after the if. And that is pointing to some kind of expression. First of all, let's make a condition node. Conditional. New statement conditional. And then we have the condition, we have the true body and the false body. So you're gonna parse an expression here. That's the expression. And that will actually stop when we have this opening curly. So we don't need to do anything more, we can just parse the true expression right away. Parse compound statements. So that should be parsing something like this. And it's going to parse everything down here. And then we have to look for the else. So here it's going to be like else. So if we have else, we're going to parse this again. Because then it's going to be like this again. Else if data. And if then we have else again, it's going to just recurse down. So let's see, if the next token here, or if the current token, we're just going to look at, if token is equal to current token if this keyword, if this token is keyword else, then we have a false body. And then we're just going to say that the false body is equal to parse if statement recursively. And we return statement condition. Else, we're going to parse this again. Actually, we have to check for the next one after that as well. So if current token is else, first we have to skip the token. And then we're gonna read the next one. If that token, is if again, it is gonna parse the if statement recursively. And that's gonna have the first token there. Yeah. And else, because we have an else, we're just going to say condition false body is equal to parse compound statement. All right, I think that's going to work. So that's the if. Yeah, so we need to print this. We need to be able to print the conditional statement. Statement conditional. That's a statement. conditional. So what are we going to print? We're going to print if without indentation first. So indented print if How can I do this nicely? I don't think I can do this nicely. It's gonna like recurse as I do in the parser. Yeah, I think so. Indentation plus plus, indentation minus minus. So we have two cases, we have true and we have false. So you can say indented print. This is the true case. And then we have the false. Okay. And also I want to print like under the if is going to be like a line down to true. So we're going to save the indentation here. Indent is equal to indentation. And we're going to paint indentation because we're going to have a true body anyway. So if indentation is equal to true. No, not really. We're gonna have like, if we have a false body, we're gonna set it to true. So if condition false, then we're setting it to true. And then we're clearing it here anyway. And then to print true, I think I'm gonna indent again. Print statement, and we're going to give it condition true body. And then we're clearing here anyway. We can clear if we have a false body. And then we're going to print the false body as well. This is happening if the condition false body is true. Oops. False. I need to print the if condition as well. So I'm going to paint it anyway up here. So I'm painting the indentation and then we're printing the condition. Indentation plus plus. That's gonna go up here. Up there. And this is an expression. All right. We're setting that to true then. We're setting it to true there. So if we have a false body, this is really gonna be like if we don't have a false body, we're gonna set it to false. We're gonna clear the indentation there. So now I should be having like an if statement. So I have a condition there. True is a compound. What the why is true? Oh. Yeah, okay. So I'm not doing anything in there. And false is a new if statement, which is checking for 4. And if that's true, it's a new compound there. So that's working. We're not doing anything in the compound then, but that's fine. So it's complaining about some typer statement not handled. So we're gonna need to type the expression and both the bodies if they exist. Type expression, type statement. So if we have an if statement, a conditional statement I'm calling it. I should call it if statement instead. Then we're just going to type the, thank you for following, expression. Conditional, condition, and where's the statement? True body. Okay, so now it's typing the program. We have a sigfault. That's because we don't have a false body. This is a conditional thing. All right. So we're not handling that statement here. So if data is equal to 4, I think data will be like 21. So I'm going to check if data is 21. Yeah, if it's working. Generator, we need to generate this. So it's very similar as what we did. Conditional. We're gonna have a static loop counter. This is gonna be an if counter. And for nested if statements, I think we need to store the number 0. That's a good point from my guy in the stream. So if counter plus plus, we're storing the current number. We really need to store where it ends, like the true or the false. We're gonna evaluate the condition first. In any way. So we're going to generate the expression. Conditional. Conditional. So we're evaluating the condition. We're going to compare it with 0. And jump if equal. Okay, so if this is equal, then the condition is false. We're gonna jump to the false part. So jump if equal, and we're gonna have like an if label. If false, and give it a number, and that's gonna be the if counter. And then we generate the, let's make the label first. If false, what am I missing here? Oh, I'm escaping that one. So if false, and we also have to check the if end actually. All right. So if this is a false thing, it's going to jump to if false. And here it's going to generate the statement for the false condition. False body. Otherwise, it's going to generate for the true body. And then when it goes down here, it has to jump to the end, because you don't want it to execute the false body here. So you want it to jump to the false body afterwards. Jump if end. Is that working? Let's see, segmentation fault. If I'm not doing this, that's working. Okay, so data is equal to something. You compare jump if false. You compare data with 21. We actually need to check this. If condition false body. Undefined reference if and one. If and one. This undefined reference to if and one. Let's take a look at the code. If and one. It says if and two. Why is that? If it's comparing and it's jumping to if and one. I'm using the if counter. Fuck. I'm supposed to use this one instead. Yeah. And then it's generating, yeah, it's working. And if I change something to, like if I change the number, it might not work. I looked through your GitHub, you have an impressive project. Thank you very much. Lower level programming too. I don't, unfortunately, I don't have any books for that. I've never read any books, so I can't really say if anything is helpful. Like for compilers, I think just looking at this project here might help. For OS, there were a very nice video on the on specifically that, the context switch, which is taken down sadly. But that was what I watched, and I looked a little bit in the Linux kernel just to get an idea on how they're doing stuff, and otherwise it's just like trying different things. Yeah. The Dragon Book. I never read that. Okay, let's see if we're gonna write something here. So I'm gonna check if I'm gonna first dereference board, and then I'm gonna access element number I and j. If this is equal to 0, I'm gonna ignore the painting. We can just say like if that's something. If this is something, I'm gonna print an X here. And else you do this. it's going to print the X anyway. And that's probably because everything is non-zero. So if I have an init function, init board, that's almost the same. I can just copy it. Taking in a board reference, and we ignore all the printing. We're just gonna set the value equal to 0. And we have to call that as well. So before we printed it, we're gonna call it init function. All right. Print board array. Is that really happening? It's not happening. We have an error. Crap. Expected something but got something else. Is this an else? And that's very hard to know because my printing is not working correctly. I feel like it might be the next line underneath this one. Oh. This is line number 18. Maybe I can turn on line numbers. This is line number 18, which is up there. It does seem to get the line number wrong. Because that's not line 18. It is expecting something. Because it can't parse anything. It was expecting this but got that. I think it is expecting this ending here. It seems like maybe the expression is ending here. So this is really parsed as a unary. This is parsed as a unary expression, and the unary thinks this is a something like sub-expression, and I think I'm returning there. Yeah, I think I'm returning there. If this is open parenthesis, I'm returning expression. That is not really true because I'm going to parse the suffix expression as well. So I'm going to try to parse the suffix expression while still using this one. And then it's working. And we have a segfault. So board is going to first dereference this. So then I have to know that I'm giving it the right thing. Oh shit. What the fuck is this? That's the function f. This is the function print board. And the body is doing something with a new loop here. So it checks if this is true. This is the one which is failing. And can see that it's taking this plus the right thing here, and it's propagating up to like the array of 3. This is a unary DRF board. Okay, so identifier so board is a pointer to this, and by dereffing that, you're gonna get this, which is correct. So where is this being called? Performing some kind of call here. Here we go. So I'm giving the address of that. So I need to know the address of this array. Where is this array stored? So I'm getting that right. That's in here, like in primary expression something. So unary, that's a primary expression. It is actually a unary expression. And if this is the address, I'm generating the address of the operand. So in my case, the operand is this. Yeah, the operand is just this, just an identifier. So I'm generating the address of an identifier, which is just loading the address. Okay, so it seems right. So what we can try to do, we can try to print whatever the address is. So I think I'm calling this first. So the address is valid, I think. And it prints okay. Where am I printing okay? I'm printing okay somewhere. Okay, so it does one okay, and then it crashes. Yeah. So the address of the board is correct. So it should be first loading the address and then dereferencing it. Index plus 1. What would index plus 1? It's quite outdated now and fails to explain concepts properly. I haven't read it, but probably someone knows. Okay, so it moves 0 into RAX. This is the comparison. And then it tries to figure out what I have to do. So this is very strange. It's starting with 8. That's weird. Let's I think I'm here. No. That's the init board. Yeah, I'm definitely here. Is that where it fails? I'm setting it to 0. That makes sense. Okay, so this is what's happening. I'm computing the right hand side first. DRF of that. Yeah, so the right hand side first, which is j times 8. So move 8, pop, multiply, here we are. So at this point we're starting with this unary deref, which is the left hand side. And this is a binary plus. And the left hand side is I and 24. Multiply I by 24, which is being done there. And then we are adding that to the board. And here it seems I'm loading this twice, which is wrong. I'm moving this into racks twice. If I'm doing this, and I type make compile, I'm getting it, almost. So I'm having this to move into RAX. And we have to figure out why. So I guess that I'm dereferencing it. That's gonna be one move, and this is gonna be one move. So that is actually correct. It's gonna move it twice. Because it's gonna move this board, like the first one, like this line is only getting the address of the board. So that's loaded so you know what the value of board is, which is supposed to be a pointer. So you're dereferencing that as well. And then you're popping RDI, you're adding those two, then you're up here, you're popping RDI, you're adding, and then you do a deref. Where is this deref going? I think I'm missing a deref, at least one deref. If this is a deref, this is, let's try to do this. It's just gonna crash. Anyway, I think I'm actually gonna quit now. I want to check one more thing. I want to check factorial. And I don't know if return expressions work. Can I return something there? I'm just placing it in RAX, so it should be possible. So I want to check the end condition, which is data equals I'm going to do like if data equals, what is the end condition, 0? Then you return the arguments. And else you return data, let's see, you return factorial of data minus 1. So this is going to be one more, like, yeah, it's going to be data times data minus 1. And that's going to eventually be called with data. That's 0. I'm going to return 1 here. Isn't this correct? 0 is not equal to 1. Isn't it supposed to be like this? If data is equal to 1, return data. So you're not going to recurse anymore. Yeah, okay. So it's going to be like this. Okay, so factorial, and just print a number. Factorial of like 8. I think that's going to be a rather big number. Factorial of 8. And then I'm returning 0 after. So what is 8 factorial? That's 4,320. 4,320. And we're getting 4,320, which is working. So recursion works, that's fine. We're just recursing like 8 times though. So that's cool. Not 0 is equal to 1, so your original was right. I guess it doesn't matter. As long as I like have either this one or this one, it is still gonna work. Because this is gonna be 1 and then it codes it with 0. And if you do like 1 times 1 or just 1, it doesn't matter. So yeah, I'm very tired. I'm like really confused here as well. But I think I'm just gonna quit now. Like, things start to come together. This is really cool. We can actually make real programs here. Loops are working, if statements. Yeah, so now we need to fix the pointer issue. I think maybe we can try again tomorrow. I have to check if I have to do some work tomorrow. But maybe I'm gonna try to stream tomorrow. And yeah, fix the pointer issue. And the next thing we want to implement is probably structures. Structures and enums. So that's gonna be interesting. And then we can actually make cool programs. And also, we can try to do some more, like maybe we can try to read something from a file or something. Like this main is getting something from the input. Let's just print what this is getting in. Isn't that like argument counts, and oops. Argument count is a U64, and then arguments, which is a pointer to char. Something like this. Yeah, this is a ref. Fuck, I'm gonna change this. I'm not kidding, I'm gonna change that to back to star again. So we get like 1 argument there. And I think that's because I'm only calling it with 1 argument. What we can do, we can try like for I in 0 to arg count -1, we're gonna just print the arguments. So this is a double char pointer. I don't know if double pointers are gonna work. We can just try and see if it works. So the argument is a string. So I'm gonna give it arguments of I. I have no idea this is gonna work. No, perfect. Args, which is a pointer to char. So Segmentation fault. Like, I'm pretty sure this is gonna act like do the right thing. This is only a deref. And argument is a pointer, but it isn't an array. So generating this unary will do this. We can verify that that's really happening. Okay, that's data. I think it's calling. That's the first. And then we have 128, which is the args. That's 128. So it's loading three times. Which doesn't really make sense. That's only going to be happening one time. So now we're getting something at the argument line. Maybe this. Okay, so there's where this is working. So if I'm now calling it with multiple arguments, it should print. So I'm running this build here. This is a test. It's printing only one. And that's probably because it's told to print only one. If I do argument and args +1. Then I'm gonna need 5 times. Yeah, okay, that makes sense. Then we have a fail. And then we're gonna fix the issue. We're gonna remove this, and then it works. We get the file, and this is a test. Okay, that's pretty cool. There is something with pointers. We're gonna try to do it again tomorrow, and then we can take a look at structures. But this is really cool. Like, see, we can actually get arguments from the input here. We can actually get arguments from the input. So it should be possible to just call C functions for reading files, and then we can actually start making a new compiler in this language. I'm probably not going to be doing that, but it is still kind of cool. But the assembly code is like beyond shit. It is so bad, like 600 lines for this simple program. That's crazy. Amazing progress. Thank you very much. We did actually do kind of well. So we have a program now. We have a language now, which is starting to come together. Midnight in Norway. Yeah, I have to go to eat some dinner first. It's only 6 p.m. Yeah, it's like 8 hours behind, or 8 hours ahead. I think 8 hours ahead, or something like that. Who set the pointers to this? They're actually the same. Is that the same? Yeah. This is a pointer to a char pointer. Who's gonna have an array with pointers again. Anyway, I think I'm gonna quit the stream. And if somebody still are on, we're gonna make a little raid. And I'm gonna try to be back tomorrow. I have to fix the code as well, because I'm coding a little bit fast on stream, and I'm not getting that much time to think when I'm coding. So I'm gonna take some time to just clean up the code a little bit. Let me see here. But it's cool. I think this is a really cool thing. Like, it's fun to program a compiler. I like that. Ay, 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 ay. Jay? Checking the beta update. That sounds cool. Second, do we have a... I'm gonna turn on the sound. Thank you for the follow, by the way. Thank you very much. I think it's just preference. Yeah. This is very cool. I'm gonna rate him. I think he's checking out like Jonathan Blow's language. Yeah, and I'm gonna be back tomorrow. Hopefully. I'm gonna really try that. All right. Okay, thank you very much for watching, and I see you tomorrow.